Let the day fall away now, like a blanket slipping slowly from the edge of a bed. Let the small worries and the unfinished lists grow soft at the edges. There is nowhere else to be right now, nothing else that needs doing. The room around you is still and quiet, and the only thing I want to offer you is a picture to rest your mind on. A small picture, a calm picture, a point of light in a very dark sky. If you were to step outside tonight, away from the street lamps and the porch lights, and look up, you would see it. High overhead, or low near the horizon depending on the time and the season, there is a steady reddish dot. It does not twinkle the way the stars twinkle. Stars are so far away that their light gets shaken and stirred by our own atmosphere, making them dance and flicker. But this light holds still. It glows with a faint warm tint, the color of a dying ember, or the blush on a peach, or the soft rust on old iron. Long before anyone knew what it was, long before anyone had a name for planets or stars or galaxies, people looked up and noticed this steady red point. They noticed it moved differently than the other lights. Night after night, it shifted its position against the fixed patterns of the stars. It wandered, and because it wandered, and because it was the color of fire and of blood, it carried weight, it carried meaning. The Babylonians, who lived in the land between two great rivers thousands of years ago, watched this red wanderer closely. They called it Nergal after their god of war and of the underworld, a name that carried both heat and destruction. They tracked its path across the sky and wrote down its movements on clay tablets, pressing wedge-shaped marks into wet mud before it dried. They saw it as a sign, a messenger of things to come on earth. Farther west, in the Nile Valley, the ancient Egyptians also watched it. They called it Har-Deker, which means the Red One. They painted it in their tomb ceilings and temple carvings, a small red disk sailing among the other wandering stars. For them, too, the color mattered. Red was the color of the desert, the color of lifeblood, the color of power and danger and vitality all mixed together. Later, the Greeks gave it another name, Ares, again for the god of war, and later still, the Romans gave it the name we use now in English, Mars, the god of war, chosen for that same dusty red color that had caught the eye of every watcher for thousands of years. A small, steady, reddish point of light. That is all it was for most of human history. A light in the dark, carrying the stories people draped over it. Stories of anger and fire and distant battles in the sky. Tonight, as you lie here with your eyes growing heavy, I want you to hold that picture in your mind. A small red world, glowing quietly in a vast dark sky. Not a headline, not a countdown clock on a launch pad, not a rushed announcement about the next big mission. Just a place. A real, physical, quiet place, hanging in the silence of space, exactly as it has done for more than 4 billion years. And the question we are going to sit with tonight, the question that has no final answer yet, is simply this. Could human beings ever live there? Could we ever make a home on that small red point of light? And the first thing to say about that question, the thing I want you to breathe into your chest and then let go, is that we do not know. We genuinely, honestly do not know. And that not knowing is not a problem to solve right now. It is not a cliffhanger. It is not a source of anxiety. It is just a quiet fact. Something we can set down on the nightstand like a book we are not finished reading. There is no rush. The question will still be there tomorrow. Tonight, we are just going to turn it over gently in our hands, like a smooth stone, and feel its weight. So let your breathing slow down. Let your eyelids fall shut if they want to. Imagine yourself lying on your back in soft grass, somewhere far from any city, on a night with no moon. The sky above you is thick with stars, so many that they look like spilled sugar across black velvet. And there, among all those sharp white pinpricks, is one point of light that does not flicker. A warm, ruddy glow, a tiny copper bead, that is Mars. It is so far away that the light you are seeing left it minutes ago, traveling across millions of kilometers of empty space to reach your eye. And yet there it is, steady and patient, as if it has been waiting for you to notice it. Imagine that you could cup your hand around that light, the way you might shield a small flame from the wind. Hold it there in your mind's eye. Feel how small it is, how quiet. All the noise of the day, all the alerts and the voices and the things that tugged at your attention, they have no reach out here. There is only the dark and this one small red point, glowing with a light that has crossed the solar system just to meet you. This is not a story about a far-off future that we have to chase. It is a story about a place that already exists, right now, in the same solar system we live in. A place that, if you had the right ship and enough time, you could travel to. You could set a course and push out from Earth and, month after patient month, watch that red point grow from a dot into a disk, and from a disk into a world. A real world with mountains and valleys and plains, with skies that turn a butterscotch color at noon, with sunsets that glow blue near the setting sun. A world that is, in some ways, almost familiar, and in other ways, completely and deeply alien. We will talk about those ways soon, about the air and the cold and the radiation, but not yet. Right now, before we get into the details and the challenges, I just want you to sit with the picture itself. The idea of Mars as a place, not a problem. A neighbor, not a headline. Think about the people who first saw that red point and gave it a name. They had no telescopes, no spacecraft, no measurements. They had only their naked eyes and their minds reaching out into the dark, trying to make sense of the lights that moved. They saw the red wanderer and they felt something. Maybe a shiver of awe, maybe a quiet curiosity. Maybe a sense that the sky was not just a distant painted dome, but a real space full of real objects, with their own natures and their own paths. That same curiosity is what eventually sent metal machines hurtling across the void to touch that red world directly. But it started with someone lying on their back, or sitting on a rooftop, or standing on a watchtower in the cool night air, just looking. Just watching that steady reddish point and wondering what it might be. You are part of that same long chain of wondering now, just by lying here and picturing it. You do not need to stay awake to solve anything. You do not need to remember any numbers or any facts. The facts will come in their own time, gently, later on. Right now there is only the image. A small red world in a dark sky. Your breathing is slow. Your body is heavy and warm against the bed. Every muscle in your face is relaxed. Your jaw is loose. Your forehead is smooth. Your shoulders are sinking down into the mattress as if the bed itself is holding you, quietly, with no demands and no hurry. The red point hangs in the dark. It does not flash. It does not call attention to itself. It simply persists, night after night, season after season, century after century. The empires that named it have all turned to dust. The Babylonians are gone. The ancient Egyptians are gone. The Romans are gone. But Mars is still there, still glowing, still following its slow path around the sun. The same light that fell on their eyes falls on ours. The same questions they asked, we are still asking. And there is something deeply calming about that, I think. The fact that some questions are so big and so hard that they outlast whole civilizations. They are not meant to be answered in a single lifetime. They are meant to be handed down like a lamp from one generation to the next. And the act of handing them down is the point. The wondering itself is the point. So tonight, if you can, let go of the need for an answer. Let the question just float there in your mind, unpressured and undemanding. Could humans ever live on Mars? Maybe, maybe not. Both possibilities are allowed to exist side by side, like two quiet sleepers in the same bed. We do not have to pick one tonight. We do not have to decide. We can just let the question be a question, as steady and as patient as the planet itself. Picture that planet now, turning slowly in the dark. It is about half the size of Earth. A world of rust-colored rock and fine red dust. It has mountains taller than any on Earth. It has canyons that stretch for thousands of kilometers. It has polar caps of ice and frozen carbon dioxide that expand and shrink with the seasons. It has two tiny moons, Phobos and Deimos, named after the horses that pulled the chariot of the war god in the old stories. Fear and panic, those names mean. But the moons themselves are nothing fearful. They are small, lumpy, grayish bodies, probably captured asteroids, barely big enough for their own gravity to pull them into round shapes. They orbit close to the planet, especially Phobos, which circles so low and so fast that it rises in the west and sets in the east twice a Martian day. A strange and gentle sight, if anyone is ever there to see it from the ground. All of this is real. All of this is happening right now, on a world that is spinning quietly in the dark, 100 million kilometers away or more. And you, lying here in your bed, are connected to it by the simple fact that you can picture it. Your mind can reach across that distance in an instant, faster than any rocket. You can stand on the red plains in your imagination and feel the fine dust under your feet. You can look up and see the sun, smaller and dimmer than it looks from Earth, hanging in a tan-colored sky. You can feel the cold biting at your imaginary suit, and hear the thin wind, and know that you are standing on another world. And then you can let all of that fade, gently, back into the calm darkness of your room, because you are not there, you are here. You are safe and warm and heavy in your bed, and there is nowhere you need to go. The red point in the sky does not mind if you fall asleep. It will still be there when you wake. It has been there for more than 4 billion years. It will be there for billions more. A few hours of sleep will not change it. A few hours of sleep will not change you, either, except to rest you and restore you and make you ready for whatever the new day brings. So let the day go. Let it fall away completely. The emails, the calls, the errands, the little tensions you have been holding in your shoulders and your jaw. They are not needed here. Here, there is only the slow, steady pulse of your own breath. There is only the weight of your body sinking into the mattress. There is only the soft, warm darkness behind your closed eyelids. And somewhere, out in that darkness, a small red world is turning. It does not make a sound. It does not send a signal. It just turns, as it has always turned, around the sun. And around it, the two tiny moons are making their silent circles, fear and panic circling a god of war. But there is no war out there. There is only stillness, only the slow drift of dust across ancient plains, only the quiet sublimation of frost at the polar caps as the seasons shift, only the faint whisper of a thin carbon dioxide wind moving across crater rims and old dry riverbeds. It is a whole world, complete and self-contained, and it asks nothing of you at all. You can rest now. You can let the image of that red point of light stay with you, a tiny warm ember in the dark of your mind. Feel your breath move in and out, slow and deep, like the slow turning of a planet. There is nothing to figure out, nothing to solve, nothing to prove. The night is long and patient, and the question we are holding, the question of whether humans could ever live there, will keep. It is a good question. It is worth asking, but it does not need an answer tonight. Tonight, the question itself is enough. The small red light in the dark is enough, and your slow, steady breathing is enough. So let the breathing continue. Let the red light glow softly in the back of your mind, and let the quiet carry you gently into sleep. The small red light glows softly in the back of your mind, and the quiet carries you not into sleep just yet, but deeper into the calm, deeper into the picture we are building together, layer by gentle layer. You are still here, still breathing slowly, still heavy and warm against the bed. And that red point is still there too, hanging in the dark of space, steady and patient. Now we can begin to ask a quieter, simpler question. Not yet whether we could live there, but something more basic. Where is it exactly? How far away is that small red light, and what does it mean to call it a neighbor? Our home, the Earth, is the third planet from the Sun. If you picture the Sun as a warm lamp in the center of a great dark room, then Earth is on the third ring out from that lamp. Mercury is the closest, right up near the heat. Venus is next, wrapped in its thick pale clouds. Then comes Earth, blue and green and full of water and air. And then, one step farther out, on the fourth ring, is Mars. Just one step beyond us, one doorway down the hall. In the grand scale of the solar system, that makes Mars our next-door neighbor. Not close the way your neighbor across the street is close, not close enough to wave to from the window, but in the vastness of space, where distances are so huge they can be hard for the mind to hold, Mars is the easiest other world to reach. It is the most visitable planet we know of. When we talk about the distance between Earth and Mars, there is no single fixed number to give. Both planets are moving. They are always moving, gliding along their own paths around the Sun, and they move at different speeds. Earth, being closer to the Sun, moves faster. It takes us about 365 days to make one full loop. Mars, farther out, moves slower, taking about 687 Earth days to complete its own loop. So the distance between the two worlds is always changing. Imagine two runners on a wide circular track, one on the inside lane and one on the outside. Sometimes they are on the same side of the track, relatively near each other. Sometimes they are on opposite sides, with the whole width of the field between them. That is how Earth and Mars move. On average, across all the different positions they can be in, the distance between Earth and Mars is about 225 million kilometers. That is a number so large it can feel slippery. 225 million kilometers. Let that settle for a moment. Light itself, the fastest thing in the universe, traveling at about 300,000 kilometers every single second, takes several minutes to cross that gap. A radio signal sent from Earth to a spacecraft at Mars, moving at the speed of light, might take anywhere from about 4 minutes to over 20 minutes to arrive, depending on where the two planets are in their orbits. The distance is not small, but in the context of the solar system, it is the smallest gap between us and any other planet that might, someday, be reachable by humans. There are moments, though, when the gap shrinks much smaller. Because both planets move in elliptical, slightly oval-shaped paths around the Sun, there are times when they swing closer to each other. This closest approach is called opposition. The word comes from astronomy, and it simply means that Mars and the Sun are on opposite sides of Earth. When Mars is at opposition, it lines up so that we are passing directly between it and the Sun. At these moments, if the timing is right and the orbits have lined up favorably, Mars can come within about 56 million kilometers of Earth. That is still an enormous distance, more than 100 times farther than the Moon is from us. But it is dramatically closer than the average. At opposition, Mars appears brighter and larger in our night sky than at any other time. It becomes that much more vivid, that much easier to see without a telescope. Ancient skywatchers certainly noticed these brightening events, these times when the red wanderer seemed to swell and intensify, as if calling a little more attention to itself. 56 million kilometers. The number is still abstract, so let me give you something to compare it to. The Moon, our closest companion in space, orbits at an average distance of about 384,000 kilometers from Earth. That is less than 500,000. The journey to the Moon, for the Apollo astronauts, took about 3 days. Mars, even at its very closest, is more than 140 times farther than the Moon. A trip to Mars is not a weekend journey. It is not even a week-long journey. With the chemical rockets we have today, the kind that burn fuel to push a spacecraft forward, a one-way trip to Mars takes roughly 7 to 9 months. 7 to 9 months of coasting through the deep dark, away from the blue sky and the green Earth, and the faces of everyone you know. 7 to 9 months of watching Earth shrink to a pale blue dot in the window, and then vanish into the black. That is what it means to call Mars our neighbor. It is the closest other world worth visiting, and yet it still requires the better part of a year just to travel there one way. Picture that journey now, not as a dramatic adventure, but as a long, slow drift. Imagine yourself in a small, quiet spacecraft, far from the noise of Earth. There is no wind in space. There is no sound outside the hull. The only thing you hear is the hum of the life support systems, the soft whir of a fan, the occasional click of a relay. Outside the window, the stars do not twinkle, because there is no atmosphere to stir their light. They are steady, sharp points, millions of them, in every direction. And ahead of you, growing so slowly you do not notice it day to day, is a reddish disk. At first it is just a dot, like the one you see from Earth. Then, after weeks and weeks, it becomes a small, distinct circle, then a larger circle, then a world, filling the window, with dark patches and white polar caps, and a thin haze of dusty air. That slow approach, that patient unfolding, is what a journey to Mars would feel like. It would not be a sudden arrival, it would be a gradual realization, a slow blooming of detail. While you are making that long crossing, you would not be entirely alone in the space around Mars. The planet has 2 small moons, companions of its own. Their names, as we touched on earlier, are Phobos and Deimos. They were discovered in the year 1877 by an American astronomer named Asaph Hall, who spent night after night at the telescope, searching the space close to Mars. When he found them, he gave them the names of the 2 horses that pulled the chariot of Ares, the Greek god of war. Phobos means fear, and Deimos means panic or terror. But the moons themselves are nothing to fear. They are small and lumpy and quiet. Phobos, the larger of the 2, is only about 22 kilometers across at its widest point. It is not round like our moon. It is shaped more like a potato, a dark and cratered rock tumbling slowly end over end. Deimos is even smaller, only about 12 kilometers across. Both are so small that their own gravity is too weak to pull them into a smooth sphere. They are probably captured asteroids, stray rocks from the belt between Mars and Jupiter that wandered too close long ago and were caught by Mars's gravity. Phobos orbits incredibly close to Mars, closer than any other moon in the solar system orbits its parent planet. It skims just a few thousand kilometers above the surface, so close that from the ground of Mars, Phobos would look quite large, a dark, irregular shape sailing rapidly across the sky. It moves so fast that, as I mentioned before, it rises in the west and sets in the east, twice every Martian day. Deimos, farther out, moves more slowly, drifting across the sky in a more familiar east-to-west direction, but it takes several days to cross from horizon to horizon. These 2 tiny moons are the only natural companions Mars has. They are not worlds anyone would ever walk on. They are more like waypoints, small dark rocks marking the approach to the red planet. If you were in that slow drifting spacecraft, you might see Phobos pass across the face of Mars, a tiny black dot crawling over the larger reddish disk. A quiet transit, a small shadow. And all of this is real. Phobos and Deimos are real places. They have been photographed up close by orbiting spacecraft. We have maps of their craters and ridges. We know their shapes and their colors, and their orbits with great precision. They are not imagined. They are there, right now, circling the red planet in the dark, the same dark that you are drifting toward, in this gentle picture we are painting together. Let your breathing stay slow. Feel the weight of your body pressing down into the bed. The journey we are describing is not one you have to make with your body. It is only a journey for the mind, a way of moving closer to understanding this neighbor world. You do not need to pack a bag or leave the room. You can just lie here, still and heavy, and let the distance numbers wash over you without needing to memorize them. 225 million kilometers on average. 56 million kilometers at the closest. 7 to 9 months with current rockets. These are just gentle markers, little signposts along the path of our imagining. They are not homework. They are not a test. They are just a way of feeling the shape of the space between us and that small red light. Think again about the fact that both worlds are moving. Right now, as you lie here, Earth is carrying you through space at about 107,000 kilometers per hour around the Sun. Mars is also moving at about 87,000 kilometers per hour. The 2 planets are like dancers on a huge dark floor, circling the same central light, sometimes drawing closer, sometimes moving apart. The gap between them is never the same from one night to the next. That means that when we talk about a trip to Mars, the timing matters enormously. You cannot just launch whenever you want. You have to wait for the right window, the right alignment, when the two planets are positioned so that a spacecraft can take the most efficient path between them. These windows open roughly every 26 months. So if you miss one, you wait more than 2 years for the next. Space travel is a practice in patience, in waiting for the slow dance of the planets to line up in your favor. All of this, the distance, the travel time, the orbital dance, is what makes Mars feel reachable at all, but only just. It is far, but not impossibly far. It is hard, but not unimaginably hard. It is the one place beyond our own moon that humans have seriously, repeatedly, planned to visit. Not to colonize tomorrow, not to terraform into a second Earth, but to visit, to touch, to stand on and look around. That is the quiet truth at the heart of this section. Mars is not just a dot in the sky, and it is not just a fantasy. It is a real place, sitting on the fourth ring from the sun, one step outward from our own, and the distance to it, while vast, is a distance we have already begun to cross with our machines. So as you lie here, with your eyes closed and your breathing deep and even, picture the solar system as a great quiet neighborhood. The sun is the warm hearth at the center. Mercury is a small hot rock close to the fire. Venus is a bright cloudy jewel on the second ring. Earth is a blue and green oasis on the third, with its one large moon circling faithfully around. And then, just beyond, on the fourth ring, is Mars. Smaller than Earth, redder, colder, quieter, with its two tiny moons, Phobos and Deimos, scurrying around it like small companions. The gap between the third ring and the fourth ring is wide, wider than any human has yet traveled. But it is not unbridgeable. It is a gap that minds have already spanned, that robot explorers have already crossed, that human eyes have already measured and mapped and imagined crossing. And now, in this quiet moment, your own mind is spanning it too. You are there, in the way that matters most right now. You are picturing the red planet turning in its orbit, with its dusty plains and its tall mountains and its thin, wispy air. You are picturing the distance not as a barrier, but as a simple fact, a measurement, something that exists calmly in the world. 225 million kilometers, on average. 7 to 9 months of quiet coasting. Phobos and Deimos keeping their silent watch. The dark of space holding it all, without urgency, without demand. Let those images drift now. Let them soften and fade, the way a reflection fades on water when the wind dies down. The numbers can fall away, the facts can rest. What remains is just the sense of Mars as a neighbor, a world next door, a place that is real and reachable and yet still deeply, profoundly far away. The red point in the sky is not just a light, it is a destination. It is a world you could, in theory, travel to. A world that sits just one ring farther from the sun than the world you are lying on right now. And that thought, that quiet thought, is enough to carry into the next layer of our picture. But for now, just rest with the distance, rest with the slow dance of the planets, rest with the image of a small red world, turning quietly on the fourth ring, with its two tiny moons, waiting patiently in the dark. The small red world turns quietly on the fourth ring, its two tiny moons waiting patiently in the dark. And now, as your breathing stays slow and even, we can draw a little closer. We can move from the distance between our world and Mars, and start to picture the world itself. What kind of place is it really? If you could stand on its surface, if you could walk across its plains and look up at its sky, what would you find beneath your feet? Before we can ask whether humans could live there, we need to know what kind of body Mars actually is. We need to build a physical picture of the planet itself. Mars is a world about half our size. That is the simplest way to say it. The diameter of Mars, which is the distance straight through its middle from one side to the other, is about 6,792 kilometers. Earth's diameter, by comparison, is about 12,742 kilometers. So if you could set the two planets side by side, like two globes on a quiet shelf, Mars would look like the smaller sibling. It would rise only to about the shoulder of Earth. Its total surface area is much smaller too. In fact, the entire surface area of Mars is roughly equal to the land area of Earth. Think about that for a moment. All the continents of Earth, all the dry ground we have spread across our blue planet, add up to about the same amount of surface as the whole of Mars. But on Earth, that land is broken into pieces, separated by vast oceans. On Mars, the whole surface is one continuous stretch of dry ground, with no seas to interrupt it. It is a single, unbroken world of rock and dust. Because Mars is smaller, its gravity is weaker. Gravity is the force that pulls everything toward the center of a planet. It is what gives weight to your body, what makes your bones and muscles work against a constant downward pull. On Earth, that pull is strong and familiar. On Mars, the pull is much gentler. The surface gravity of Mars is about 38% of Earth's. That means if you weighed 100 pounds on Earth, you would weigh only 38 pounds on Mars. If you could step onto a bathroom scale on the red planet, the number would be less than half of what it reads at home. You would feel light on your feet. Your arms would swing easily. Every step would carry you higher and farther than it does here. Jumping would feel almost dreamlike, a slow rise and a softer landing. This lightness would be one of the first things an astronaut would notice, after months of weightlessness in the spacecraft, finally standing on solid ground again, but feeling only a fraction of the familiar pull. That word, gravity, is one we will return to later in more depth, especially when we talk about what low gravity might do to a human body over long periods of time. But for now, just hold the sensation in your imagination. Picture yourself standing on a wide red plain under a dark sky. Your body feels light, almost buoyant. Each breath you take comes from a tank on your back, because the air outside is not breathable. But your limbs move easily. The ground under your boots is firm and dusty, but it does not hold you down the way Earth ground does. You could pick up a rock that would be heavy on Earth and find it surprisingly easy to lift. This is the physical reality of Mars, a world where everything weighs less, simply because the planet itself is smaller. Even though Mars is half our size, its day is remarkably similar to ours. A day on Mars, measured from one sunrise to the next, lasts about 24 hours and 39 minutes. Scientists who study Mars call this a sol, a word that simply means a Martian day. 24 hours and 39 minutes. That is so close to Earth's 24 hours that the human body would barely notice the difference. The circadian rhythms, the internal clock that tells us when to sleep and when to wake, would find the Martian day almost perfectly natural. This is a quiet but important fact. It means that any humans who did travel to Mars would not have to fight against a radically different day length. They could keep a schedule that feels, in its basic structure, like home. They could sleep at night and work during the daylight with only a slight adjustment for the extra 39 minutes. Compare that to Venus, where a single day lasts longer than an entire Venusian year, or to the Moon, where a day lasts 14 Earth days followed by 14 Earth days of night. Mars, in its day length, is almost kind, almost gentle. It offers a rhythm that our bodies might slip into without great struggle. But if the Martian day feels familiar, the Martian year is a different story. A year is the time it takes a planet to make one full orbit around the Sun. On Earth, that takes about 365 days. On Mars, it takes about 687 Earth days. That is almost twice as long. A Martian year is nearly 2 Earth years long. So the seasons on Mars, which come from the same reason as seasons on Earth, stretch out and linger in a way we are not used to. And what is that reason? Why do planets have seasons at all? It is because the planet is tilted. Earth spins on an axis that is tilted about 23.5 degrees from straight up and down. That tilt means that as Earth orbits the Sun, sometimes the northern half leans toward the Sun, getting more direct sunlight and warmth, and sometimes it leans away, getting less. That leaning is what gives us summer and winter. Mars spins on a tilted axis too, and its tilt is about 25 degrees. That is very close to Earth's tilt, 25 degrees compared to 23.5. So Mars has seasons in much the same way we do, for the same reason. The northern hemisphere of Mars has a summer when it leans toward the sun, and a winter when it leans away. The southern hemisphere has the opposite. But because the Martian year is so much longer, each season lasts much longer. A Martian spring does not last 3 months. It lasts closer to 6 months, by Earth's calendar. A Martian winter stretches on for half an Earth year or more, and the seasons are not all the same length as each other, because the orbit of Mars is more oval-shaped, more elliptical, than Earth's orbit. Earth's orbit is nearly a perfect circle. Mars's orbit is noticeably stretched. That means Mars moves faster when it is closer to the Sun and slower when it is farther away. The southern hemisphere of Mars happens to be tilted toward the Sun during the closest part of the orbit, so southern summers on Mars are shorter and hotter than northern summers. Northern summers are longer and milder. These are gentle details, quiet facts about a distant world. They are not things you need to memorize. They are just textures, small threads in the picture we are weaving. Picture those seasons unfolding on the red planet. A long, slow spring in the northern hemisphere, with the polar ice cap shrinking back as frozen carbon dioxide turns directly to gas and drifts into the thin air. A lingering summer where the midday temperatures at the equator might, just barely, rise above the freezing point of water. A long autumn with dust storms beginning to stir as the temperature shifts. And a deep, prolonged winter, with the polar cap growing again, spreading a layer of frost across the high latitudes. All of this happening at a pace that would feel, to a human observer, stretched and strange. The same season lasting month after month after month. No rush, no hurry. The planet taking its time, as it has for billions of years. The tilt of Mars, like Earth's tilt, also means there are places on the planet that experience long periods of continuous daylight or continuous darkness near the poles. On Earth, above the Arctic Circle, the sun does not set for weeks in the summer. On Mars, the same thing happens at the poles, but for much longer stretches. A polar summer on Mars might have the sun circling the sky without ever dipping below the horizon for months on end. A polar winter might be an equally long night. These are extreme places, not where any early visitors would likely settle, but they are part of the planet's physical character, part of what makes it a real world with its own rhythms and patterns. So let us gather the picture we have so far. Mars is about half the diameter of Earth, with a surface area roughly equal to all of Earth's dry land put together. Its gravity is a gentle 38% of ours, so everything weighs much less. Its day is almost the same length as an Earth day, off by only 39 minutes. Its year is nearly twice as long, with seasons that stretch out slowly. Its axis is tilted, giving it summer and winter, northern and southern differences. All of this is known. All of this is measured. Spacecraft orbiting Mars have mapped its surface in extraordinary detail. We know the height of its mountains and the depth of its canyons. We know the shape of its gravitational field, the slight variations in its pull from place to place. We know its size, its mass, its tilt, its spin. These are not guesses. These are facts, gathered over decades of careful observation, first by telescopes and then by probes that flew past, then by orbiters that circled, then by landers that touched down and sent data back. And yet, for all these facts, Mars remains a place no human has ever stood. Every number I have given you comes from instruments, not from direct human experience. The diameter of 6,792 kilometers was not measured by a human hand stretching a tape across the planet. It was calculated from images and radar and orbital data. The gravity at 38% was not felt by human legs jumping on the surface. It was inferred from the planet's mass and size. The seasons were not watched by human eyes from the ground, noticing the slow change in the sun's angle. They were photographed by orbiting cameras over many Martian years. All of our knowledge is second-hand, relayed through machines. This is not a disappointment, it is simply the state of things. It means that when the first human finally does stand on Mars, everything they experience will be a confirmation, a closing of the gap between the numbers and the feeling. They will feel that 38% gravity in their bones, not just read it on a screen. They will watch the sun creep across the tan sky and know, in their body, that the day is 39 minutes longer than the one they grew up with. That day has not come yet. No one knows when it will. But the planet is there, waiting, exactly as described. A world half our size, with a gentle pull and a familiar daily rhythm. A world where the seasons are long and the years are deep. A world of rust-colored rock and fine dust, spinning quietly in the dark, one step farther from the sun than we are. You can hold that picture in your mind as you lie here. You can feel the smallness of the planet, the lightness of its gravity, the slow turn of its day. You can imagine the dust settling on a plain under a tan sky, with no one there to see it. The planet does not need an audience. It just exists, turning and tilting, cycling through its long seasons, as it has for more than 4 billion years. The numbers and the facts are just ways of letting our minds touch it from across the distance. And now, as your breathing stays deep and your body stays heavy, you can let the numbers soften. You can let them become a feeling instead of a list, a sense of Mars as a real place, with its own size and its own time and its own quiet rhythms, waiting in the dark for a visit that has not yet come. Mars waits in the dark, a real place with its own size and its own quiet rhythms. And now we come to something that sets it apart from Earth in the most immediate way: the air, or rather, the lack of it. If you were to step onto the surface of Mars without protection, the very first thing you would notice is not the cold, not the color of the sky, not the lightness of your body. The very first thing you would notice is that you cannot breathe. There is simply not enough air, and what little air there is the wrong kind. This is the single most immediate reason Mars is hostile to unprotected human life. Not the cold, not the radiation, the air itself. It is thin, it is wrong for our lungs, and it would not keep us alive for more than a few moments. Let us start with something we all understand: air. The stuff that fills your lungs right now, as you lie here breathing slowly in the dark. Every time you breathe in, you draw a mixture of gases into your body. Most of it, about 78%, is nitrogen, about 21% is oxygen. The remaining 1% is a mix of other gases, including argon and carbon dioxide, and tiny traces of other things. This mixture is held around our planet by gravity, forming a thick blanket of air that we call the atmosphere. The atmosphere is what makes the sky blue during the day. It is what carries the warmth of the sun around the planet. It is what protects us from the harshness of space. And on Earth, this atmosphere is thick and heavy. At sea level, the weight of all that air pressing down on every square inch of your body is what we call air pressure. You do not feel it because your body is used to it, pushing back with the same pressure from the inside. But it is there, a steady and reassuring weight, the breathable ocean we live at the bottom of. Now, let us turn to Mars. Mars also has an atmosphere. There is air there, of a kind. But it is vanishingly thin compared to ours. The air pressure on the surface of Mars is less than 1% of what it is on Earth at sea level. To give you a number, the average air pressure on Earth at sea level is about 1,013 millibars. On Mars, the average surface air pressure is about 6 millibars. 6, compared to more than 1,000. It is as if someone took the thick blanket of Earth's atmosphere and stretched it out until it became a thin, ghostly sheet, barely there at all. If you could stand on Mars and hold out your hand, the air around it would be so thin that it would feel almost like a vacuum. The air pressure on Mars is so low that it is similar to the pressure found at an altitude of about 35 kilometers above the surface of Earth. That is far higher than any bird can fly, far higher than any cloud forms. It is into the stratosphere and beyond. It is the edge of space. What does this mean for a human body? It means that without a pressure suit, a sealed suit that keeps a layer of breathable air at the right pressure against your skin, your body would begin to fail very quickly. The low pressure would cause the fluids in your body to behave in ways they are not meant to. Water, and the liquids in your body that are mostly water, boil at lower temperatures when the air pressure is lower. On Mars, the pressure is so low that the boiling point of water drops below the normal temperature of the human body. This means that exposed bodily fluids, like the moisture in your mouth and on your eyes and deep inside your lungs, would begin to vaporize. They would turn to gas, right there inside you. This is not a dramatic explosion the way some stories might suggest. It would be a quiet, rapid, and deeply lethal process. Within a minute or two, you would lose consciousness from lack of oxygen. Shortly after, your body would shut down entirely. There is no rescue from this. There is no holding your breath and hoping to last a few more seconds. In fact, holding your breath would make things worse, because the low pressure would cause the air trapped in your lungs to expand and damage the delicate tissues. The only way to survive on the surface of Mars, even for a moment, is inside a sealed, pressurized environment, a spacesuit, a habitat, a vehicle with thick walls and a life support system. You must bring your own air, at your own pressure, or you will not last. So that is the first fact about the Martian atmosphere. It is too thin for us. But there is a second fact, and it is just as important. The Martian atmosphere is made of the wrong stuff. Even if the pressure were higher, even if the air were thick enough to keep our bodies from failing, we still could not breathe it. The air on Mars is mostly carbon dioxide. About 95% of it, in fact. Carbon dioxide is what we breathe out. Our bodies produce it as a waste product when we use oxygen to make energy. On Earth, carbon dioxide makes up a tiny fraction of the air, about 0.04%. On Mars, it is the dominant gas. The remaining 5% of the Martian atmosphere is mostly nitrogen and argon, with only trace amounts of oxygen. Trace amounts meaning far, far less than 1%. There is essentially no free oxygen to breathe. So even if you could somehow withstand the low pressure, your lungs would find nothing in the Martian air that your body can use. You would breathe in and out, and feel as if you were suffocating, because you would be. The carbon dioxide would give you no life. Your blood would carry no fresh oxygen to your brain or your heart. You would fade quickly. This combination, the low pressure and the carbon dioxide air, makes the Martian atmosphere one of the most immediately hostile environments a human could encounter. It is not a place where you can just bundle up against the cold and tough it out. It is a place where the very air around you is, for all practical purposes, a poison and a vacuum at the same time. This is not a matter of debate. It is measured fact. Every lander that has touched down on Mars has carried instruments to measure the air pressure and the air composition. The numbers are consistent. The atmosphere is thin. The atmosphere is carbon dioxide. There is no breathable oxygen. These are not problems that can be solved by simply adapting or getting used to them. They are physical realities that require hard engineering solutions. Any human on Mars will live inside a bubble of Earth-like air, a small pocket of home carried across millions of kilometers of space. Step outside that bubble without protection, and the environment will kill you. Quietly, efficiently, without malice. It is just the way the world works there. There is one more thing the thin atmosphere cannot do. It cannot shield the surface from certain kinds of light coming from the sun and from deep space. I am talking here about ultraviolet radiation, which is a kind of light that is invisible to our eyes, but carries enough energy to damage living tissue. On Earth, our thick atmosphere does many jobs, and one of them is to absorb and block most of the ultraviolet radiation that comes from the sun. The ozone layer, a special region high in our atmosphere, is particularly good at this. It acts like a gentle filter, letting through the visible light that brightens our days and warms our skin, but stopping most of the harmful ultraviolet rays. Without that filter, life on Earth's surface would be in constant danger of cellular damage. Sunburns would be far more severe, Skin cancers would be more common. Eyes would suffer damage over time. Plants and animals would struggle. On Mars, that filter does not exist. The atmosphere is simply too thin to do the job. Ultraviolet radiation from the sun reaches the surface of Mars with much greater intensity than it reaches the surface of Earth. Anyone walking on the surface of Mars, even in a pressure suit that gave them air to breathe, would need protection from this ultraviolet light. The suit itself would have to block it. The visor of the helmet would have to be treated or coated. Any habitat on the surface would need walls that could stop ultraviolet rays from coming through the windows. This is a known challenge, and it is one that engineers take seriously in every design they propose. It is not an unsolvable problem. Materials exist that can block ultraviolet light, but it is another layer of hostility, another item on the long list of things the Martian environment does that would quietly, steadily harm an unprotected human. Let all of this settle for a moment. Let the picture come into focus. You are still lying here, warm and safe in your bed, breathing the thick, rich, oxygen-filled air of Earth. Your body does not have to think about breathing. It just happens, in and out, all night long, without your attention. On Mars, that simple act, the act of breathing, would be impossible. The air is too thin. The air is carbon dioxide. The ultraviolet light beats down on the dusty surface. To step outside on Mars is to step into an environment that is, for a human, not much different from stepping into the void of space itself. The only difference is that there is a ground to stand on, and a faint wind that sometimes stirs the dust, and a sky that glows with a strange tan color. But the air will not save you. The air will not help you. The air is not enough. This is why the question of living on Mars is so hard. It is not just about distance or gravity or water. It starts with the very first thing a living body needs: air. And on Mars, there is no air that we can use. Every breath a human takes on Mars will have to be manufactured, supplied, and sealed inside a container. Every moment spent outside a habitat will be spent inside a suit that is, in effect, a tiny personal spacecraft. There is no walking barefoot through a Martian meadow. There is no standing on a hill and feeling the wind on your face. The wind is there, thin and cold, but it cannot touch your skin. If it did, your skin would feel the sting of low pressure and ultraviolet light at the same time. The romance of a new world, if it exists, will be experienced through layers of protective material, through glass visors, through the hum of a life support pump. And yet, this is also what makes the idea of going there so quietly profound. The challenge is not a mystery. We know exactly what the air on Mars is like. We have measured it. We understand it. The question is whether we can build machines and habitats reliable enough to keep a thin bubble of Earth alive in the middle of that hostile vastness. That is an engineering question, a human question, a question of patience and care and redundancy. It is not a question of whether Mars will ever change its nature to welcome us. It will not. The atmosphere of Mars is what it is, and it has been that way for a very long time. It will not thicken or sweeten for our arrival. We will have to bring our own air, or learn to make it from the local materials. And making it, as we will talk about later, is possible in small ways. But the larger truth remains. The air on Mars is not enough. It will never be enough on its own. Any life we build there will be a life inside a shell, a life that depends entirely on the machines that keep the shell intact. So as you lie here, breathing easily in the dark, let the contrast sit with you. Feel the gentle rise and fall of your chest. Feel the air moving in and out of your lungs, effortlessly, silently, doing its work. That air is a gift of this planet, a product of billions of years of life and chemistry and geology. It is thick and warm and full of oxygen. It holds you, presses around you, keeps you alive without a single thought on your part. On Mars, none of that is true. On Mars, every breath would be a deliberate act of technology. Every lungful of air would come from a tank or a recycler or a carefully grown plant inside a sealed greenhouse. The simple, unthinking ease of being alive on Earth would be replaced by a constant, low-level awareness of your own fragility. This is not to say it is impossible, it is only to say that it is different. Fundamentally, deeply different. And that difference begins with the air, the thin, cold, carbon dioxide air of Mars, the air that is not enough. Let your breathing continue, slow and deep. Let the weight of your own atmosphere, the one you live in without thinking about it, be a comfort. You are here. You are breathing. The air is good. And out there, on the fourth ring, the thin winds of Mars are blowing across empty plains, carrying dust and cold, waiting for a visitor who has not yet arrived. That visitor will come someday, sealed inside a suit, carrying a small piece of earth in their lungs. But that day is not tonight. Tonight there is only the quiet, and your slow breathing, and the picture of a world where the air is not enough, turning silently under a tan sky. The thin winds of Mars blow across empty plains, carrying dust and cold. The air is not enough, and the world turns silently under a tan sky. Now we can step a little closer still, and ask what it would actually feel like to stand on that surface. Not the air in your lungs, which we have already talked about, but the feeling on your skin, the temperature, the light, the color of the sky above you. These are the sensory details, the things a human standing on Mars would experience through the walls of a suit or the window of a habitat. And they paint a picture of a world that is, in some ways, almost recognizable, and in other ways, deeply strange. Let us begin with the cold. Mars is a cold place. Not cold the way a winter night on Earth is cold, but cold in a deeper, more persistent way. The average surface temperature on Mars is around -63 degrees Celsius. That is about -81 degrees Fahrenheit. That is the average, the middle point across all the locations and all the seasons and all the times of day. It is colder than the coldest places on Earth where people live. It is cold enough that carbon dioxide, the main gas in the Martian air, sometimes freezes directly into a solid, forming frost on the ground and at the polar caps. This is a world where the very air can freeze. But that average hides a wide range. Temperatures on Mars vary a great deal, depending on where you are and what time of day it is and what season it is. Near the equator, at midday in the height of summer, the surface temperature can actually rise above the freezing point of water. Just barely. It might reach a few degrees above 0 Celsius, perhaps as high as 20 degrees Celsius, in the most favorable spots, at the most favorable times. 20 degrees Celsius is a pleasant room temperature on Earth, so for a brief window, on a summer afternoon near the Martian equator, the ground under your boots might feel almost warm. But that warmth is thin and fleeting. It sits right at the surface, heated by the weak sunlight, and it vanishes as soon as the sun begins to set. The air itself, being so thin, holds almost no heat. On Earth, the thick atmosphere acts like a blanket, trapping warmth and spreading it around. On Mars, the thin atmosphere cannot do that job. So even on a day when the ground warms up to a comfortable temperature, the air just a few feet above the ground is still bitterly cold. You could have warm feet and a freezing nose at the same time. The difference between sun and shade on Mars is extreme, because the air cannot smooth it out. And then comes the night. When the sun sets on Mars, the temperature plunges. It drops by dozens of degrees in a matter of hours. A typical nighttime temperature, even near the equator, might fall to -70 or -80 degrees Celsius. At the poles, in the depths of winter, temperatures can drop below -120 degrees Celsius. These are temperatures that would freeze almost anything. Metals become brittle, lubricants turn solid, electronics have to be heated just to keep working. Any human on the surface must be wrapped in layers of insulation and active heating, not just for comfort but for survival. The suit or the habitat is not just keeping air in, it is keeping the cold out, fighting a constant battle against a world that wants to pull all the warmth away. This cold is relentless. It does not have the drama of a blizzard or the howl of a winter storm. The wind on Mars, even when it kicks up dust, is thin and weak by Earth standards. It could not knock you over. It would not roar in your ears. But it would carry the cold with it, seeping into every crack and seam, pulling heat away from any surface it touched. The cold is quiet. It is patient. It is always there, waiting just on the other side of the thin walls. This is one of the great challenges that any long-term settlement would have to solve. How do you keep warm on a world where the very ground is frozen deep, where the air steals heat with every gust, where the night is a plunge into temperatures that would kill an unprotected human in minutes? Now let us turn from the cold to the light. Mars is farther from the sun than Earth is, and that means the sunlight there is dimmer. On average, Mars receives about half as much sunlight as Earth does. If you stood on the surface at noon and looked up, the sun would appear noticeably smaller in the sky than it does from your backyard. It would still be the brightest thing in the sky by far, a brilliant white-gold disk, but it would be a smaller disk, and its warmth would feel thinner on your upturned face, if you could feel it at all through the suit. The light would have a different quality to it, a little weaker, a little more distant, as if the sun had stepped back just a few paces and was watching from farther away. This lower sunlight has many effects. It affects the temperature, as we have already said. It affects the amount of energy available for any solar-powered equipment. Solar panels on Mars receive less power than they would on Earth, so you need more of them, or more efficient ones, to run the same machines. It also affects the psychology of anyone living there. The dimmer sun, the longer shadows, the different color of the sky, all of these would work on the mind over time. We are used to a bright yellow sun in a blue sky. On Mars, the sun is smaller and whiter, and the sky is not blue at all. What color is the Martian sky? That is one of the most common questions people ask, and the answer, based on the images sent back by the rovers, is that the Martian sky is a kind of warm tan or butterscotch color. Sometimes it looks more yellowish, sometimes it has a pinkish or brownish tint. The reason for this strange color is dust. Fine red dust, suspended in the thin air, scatters the light. On Earth, our atmosphere scatters blue light more than other colors, which is why the sky looks blue on a clear day. On Mars, the dust particles are larger and they scatter light differently, pulling the colors toward the red and brown end of the spectrum. So the sky itself, the broad dome overhead, glows with a soft butterscotch hue. It is not a threatening color. It is almost warm, almost gentle, but it is also deeply alien. A human standing on Mars and looking up would see a sky that no photograph from Earth could quite prepare them for. A tan sky with a small white sun and the red ground stretching away in all directions. And then there are the sunsets. The sunsets on Mars are, by many accounts, one of the most beautiful and unexpected sights the rovers have captured. Here on Earth, a sunset is warm. Reds, oranges, pinks, purples, the colors of fire and flowers. On Mars, the sunset is cool. Near the setting sun, the sky turns a soft blue. The opposite of Earth. Instead of a warm glow spreading around the sun as it sinks toward the horizon, there is a cool bluish halo. The rest of the sky might take on deeper shades of brown or rust, but right next to the sun, the light scatters in such a way that the color shifts to blue. This happens because of the same fine dust that makes the daytime sky tan. The dust particles are just the right size to scatter blue light forward when the sun is low, while letting the redder light pass through. The result is a quiet, cool-toned sunset, a blue goodbye to the day. Imagine standing on a ridge, looking west across a vast, rust-colored plain. The sun is small and white and sinking. Around it, the sky fades from tan to a pale, dusty blue. The ground is dimming, and the cold is already beginning to bite harder, even though the sun is still above the horizon. The shadows are long and sharp. Everything is still. There is no bird song, no rustle of leaves, no distant sound of water. Only the thin wind, if it is blowing, a faint whisper against the rocks. That is a Martian evening. That is what a visitor would see. It is strange. It is quiet. It is, in its own way, deeply peaceful. The dust that colors the sky also colors everything else. The surface of Mars is covered in fine red dust, rich in iron oxides, which is the same thing as rust. This dust gets everywhere. It is kicked up by the thin winds. It coats the rocks and the plains and the mountains. It would coat any human habitat, any rover, any piece of equipment left outside. It would stick to spacesuits and get trapped inside airlocks. Managing that dust is one of the practical problems that any real mission would have to deal with. It is abrasive. It is pervasive. It is part of the environment in a way that cannot be avoided. The red dust is Mars, and Mars is the red dust. The two are the same. Let us put all of this together now, into a single picture. You are standing on Mars, inside a pressurized suit. The suit is thick and insulated, with heaters running to keep the cold at bay. You can hear the soft hum of the life support system, the fan circulating air through your helmet. You look down at your boots, and they are already coated in a fine layer of reddish dust. You look up, and the sky is a warm tan, almost the color of a very old paper. The sun is a small white disk, high overhead if it is midday, and its light feels thin on your suit, like a pale warmth you can barely sense. Around you, the ground stretches away, rolling and rocky, with low hills on the horizon. Everything is some shade of red or brown or rust, a whole world painted in iron. The air, if you could feel it, is bitterly cold. You cannot feel it, sealed inside your suit, but you know it is there, pressing in with its low pressure and its carbon dioxide and its deep chill. The only sound is your own breathing and the hum of the machine that keeps you alive. And then, as you stand there, you notice something. The horizon is a little too close. Because Mars is smaller than Earth, the curve of the planet is more pronounced. On flat ground on Earth, the horizon is about 5 kilometers away, for a person of average height. On Mars, because the planet is half our size, the horizon is closer. It is only about 3.5 kilometers away. The world feels a little smaller under your feet. The distances are a little shorter. The curve of the planet is a little sharper. It is a subtle thing, not something you would immediately notice, but it would be there, a quiet reminder that you are standing on a world not your own. All of this, the cold and the dim light and the tan sky and the blue sunsets and the red dust, is the sensory reality of Mars. It is not a dead world in the sense of being featureless or boring. It is full of detail, full of texture, full of quiet beauty. But it is a beauty that does not welcome the human body. It is a beauty that must be observed from behind glass, from inside a suit, from within the warm bubble of a life support system. The cold would kill you, the thin air would kill you, the ultraviolet light would damage you, and yet, the planet itself, in its colors and its light and its long, slow rhythms, has a kind of calm to it, a kind of stillness that no place on Earth quite matches. Picture that stillness now as you lie here. Picture the long shadows of a Martian afternoon stretching across the red plains. Picture the dust settling, grain by grain, after a thin wind has passed. Picture the sun, small and white, sliding down toward the horizon, and the sky around it slowly shifting from tan to a pale, dusty blue. The temperature is dropping. The stars are beginning to come out, even before the sun is fully gone, because the atmosphere is so thin that it does not scatter much twilight. The night comes quickly on Mars, and when it comes, it is very dark and very cold and very still. No one is there to see it. The plains are empty. The sky turns and turns. The small red world waits, as it has always waited, for a visitor who has not yet arrived. Let your own stillness mirror that stillness now. Let your breathing be the only sound, slow and deep. The cold of Mars is far away. The tan sky is far away. You are here, warm and safe, in your bed. And the image in your mind, the image of that quiet red world under its butterscotch sky, can just float there, soft and undemanding, as you drift toward sleep. The image of that quiet red world under its butterscotch sky floats soft and undemanding in your mind. You are warm and safe, and your breathing is slow and deep. Now we need to talk about something invisible, something that does not show up in photographs and cannot be felt on the skin, at least not in the moment. It is a danger that would matter enormously for anyone who tried to live on Mars for a long time. It is not the cold, and it is not the thin air. It is something that arrives from space itself, silently and constantly, and it is one of the hardest challenges to solve. To understand this invisible danger, we first need to understand what protects us here on Earth. Every day, every hour, every second, our planet is being hit by radiation from space. This radiation comes from two main sources. The first source is the sun. The sun is a giant ball of nuclear fire, and it does not just give off visible light and warmth. It also gives off a constant stream of tiny, fast-moving particles, and sometimes it throws out much larger bursts of energy during solar storms. The second source is everything else in the universe. Far beyond our solar system, distant exploding stars and other high-energy events send out particles that travel across the galaxy. These are called cosmic rays, though they are not really rays in the way a beam of light is a ray. They are tiny bits of matter moving at incredible speeds, and they carry a great deal of energy. If all of this radiation reached the surface of Earth at full strength, life here would have a very hard time. Prolonged exposure to high-energy radiation damages living cells. It can break apart the delicate machinery inside our cells, including the long molecules of DNA that carry our genetic instructions. Over time, this damage can lead to sickness, to an increased chance of cancers, and to other health problems that build up slowly across months and years. But here on Earth, most of this radiation does not reach us. We have two powerful shields working together. The first shield is our atmosphere. The thick blanket of air that surrounds Earth does more than just give us oxygen to breathe and a blue sky to look at. It also absorbs and deflects a large portion of the incoming radiation. When high-energy particles from space hit the top of the atmosphere, they collide with the atoms and molecules of air. These collisions use up the energy of the incoming particles, breaking them apart or slowing them down, so that by the time they reach the ground, they have lost most of their harmful power. The atmosphere is like a thick protective coat, taking the hits so that we do not have to. The second shield is something we cannot see or feel, but it is all around us. Deep inside the Earth, there is a core of hot, liquid metal, mostly iron and nickel. As this liquid metal moves and churns, it creates a vast magnetic field that extends far out into space around our planet. This magnetic field is called the magnetosphere. You can picture it as a huge invisible bubble, shaped a bit like a donut or a stretched-out teardrop, with the Earth at the center. When charged particles from the Sun or from deep space come toward Earth, they encounter this magnetic field. Because the particles themselves carry an electric charge, the magnetic field pushes them aside, steering them away from the planet, channeling them around and past us. Some particles get trapped in belts high above the atmosphere, which are called the Van Allen belts, but very few make it all the way down to where we live. Together, the thick atmosphere and the strong magnetosphere form a double layer of protection. They have allowed life to thrive on the surface of Earth for billions of years, shielded from the constant rain of radiation that fills the solar system. We do not notice this protection. We are born into it, we live our whole lives inside it, and we never have to think about it. But it is there, quietly doing its work, every moment of every day. Now, let us turn back to Mars. Mars does not have these shields. Billions of years ago, early in its history, Mars is believed to have had a stronger, hotter interior, and it likely generated its own global magnetic field, much like Earth does today. But Mars is smaller than Earth, and its interior cooled more quickly. At some point, perhaps around 4 billion years ago, the churning of the liquid metal core slowed and stopped. When it stopped, the global magnetic field faded away. The magnetosphere, the invisible protective bubble, was gone. Today, Mars does not have a planet-wide magnetic field. It has only weak, scattered patches of magnetic rock in some parts of its crust, leftover remnants of that ancient field. These local patches are not enough to shield the whole planet. They are like a few tattered scraps of an old coat, offering no real protection. Without a magnetosphere, the surface of Mars is much more exposed to what comes from space. The solar wind, that constant stream of charged particles from the Sun, reaches the upper atmosphere of Mars directly. Over billions of years, it has helped strip away much of what was once a thicker Martian atmosphere, carrying gas molecules off into space. And the radiation, both from the Sun and from cosmic sources, reaches the surface with far less in the way. The thin atmosphere of Mars does absorb some of it. Every little bit of air helps. But with less than 1% of the air pressure of Earth, that protection is very limited. The radiation environment on the surface of Mars is significantly more intense than what we experience on Earth. How much more intense? We have direct measurements. The Curiosity rover, which landed on Mars in the year 2012, has been carrying an instrument specifically designed to measure radiation on the Martian surface. This instrument, called the Radiation Assessment Detector, or RAD for short, has been recording the types and amounts of radiation reaching the rover for years now. The data it has sent back give us a clear picture. The radiation dose on the surface of Mars is not astronomically high in the short term. It is not like standing next to a nuclear reactor. A human standing on Mars for a day or a week would receive a radiation dose that is elevated compared to Earth, but not immediately dangerous. The problem is not a day. The problem is months and years. A long-term stay on Mars, of the kind required for any serious settlement or extended exploration mission, would accumulate a significant radiation dose over time. The exact amount depends on many factors. The solar cycle, for instance, makes a difference. The Sun goes through periods of higher and lower activity in a cycle that lasts about 11 years. During times of high solar activity, the Sun sends out more particle radiation, but it also sends out stronger magnetic fields that can actually help block some of the cosmic rays coming from outside the solar system. During times of low solar activity, the opposite happens. The location on Mars also matters. Higher altitudes, where the atmosphere is even thinner, receive more radiation than lower altitudes. The deepest parts of the giant impact basin, called Hellas Planitia, which is one of the lowest places on Mars, might offer slightly more protection than the high plains. But regardless of these variations, the overall picture is clear. The surface of Mars is bathed in a level of radiation that is much higher than Earth's surface. Anyone living there for years would be exposed to a cumulative dose that raises real health questions. And here is where we must be very honest. The long-term health effects of this kind of radiation exposure on the human body are not fully known. This is not a solved problem. It is not something where we can look up the answer in a textbook and be done with it. The RAD instrument on Curiosity has given us excellent data on what the radiation environment actually is. But that data has to be translated into predictions about human health, and that translation is difficult. Most of what we know about radiation health risks comes from studies done on Earth, studies of survivors of nuclear events, studies of workers in certain industries, studies of patients who received radiation as part of medical treatments. These studies tell us that radiation increases the risk of cancer over a lifetime. They tell us that it can damage the nervous system and the cardiovascular system. They tell us that the effects are probabilistic, meaning that not everyone exposed will get sick, but the chances go up with the dose. The problem is that the radiation environment on Mars is different from the radiation environments studied on Earth. The mix of particle types is different. The energies are different. The rate of exposure, spread out over months and years rather than delivered all at once, is different. How all of these differences affect the human body is not yet well understood. Furthermore, there are effects beyond cancer. There is some evidence, from studies of astronauts and from laboratory research, that radiation can affect the brain and the central nervous system over time. It might contribute to cognitive decline, memory problems, or changes in mood and behavior. These are subtle effects, hard to measure, hard to separate from all the other stresses of living in space or on another planet. But they are real concerns, and they are actively being studied. The simple truth is that no human has ever lived on Mars. No human has ever spent years exposed to the radiation environment of the Martian surface. All of our understanding is based on models, on data from robots, and on comparisons to situations on Earth that are not exact matches. Scientists openly acknowledge this as a real gap in knowledge. It is not a secret. It is not a scandal. It is just something we do not yet know. What does this mean for the question we are sitting with tonight? The question of whether humans could ever live on Mars. It means that radiation is one of the biggest obstacles. It is an obstacle that cannot be negotiated with. You cannot ask the radiation to stop. You cannot reason with it or adapt to it. You have to shield against it. And shielding is heavy. On Earth, we are shielded by the atmosphere and the magnetosphere without having to think about it. On Mars, any shield would have to be built. Thick walls of rock or soil or ice, underground habitats, specially designed materials. All of these add weight and complexity and cost to any mission. They make the engineering harder. They make the logistics harder. They are not impossible in theory, but they are very difficult in practice. And then there is the journey itself. The 7 to 9 months of travel between Earth and Mars would also expose astronauts to radiation. The spacecraft would be outside Earth's magnetosphere for most of the trip, coasting through interplanetary space, where the radiation environment is even more intense than on the surface of Mars. Solar storms, if they occurred during the journey, could deliver a sudden high dose unless the spacecraft had a dedicated storm shelter, a small shielded area where the crew could retreat for a few hours or days. All of this is part of the same problem. The invisible rain of particles from the sun and from the galaxy does not stop. It is always there, and it must be accounted for. So as you lie here in the dark, with your breathing slow and steady, consider the invisible shields that protect you right now. The thick air above you, pressing down, absorbing radiation. The vast magnetic field, generated by the churning metal deep inside the Earth, deflecting particles away. You are living inside a protected bubble, a rare and precious thing in the solar system. On Mars, that bubble is gone. The air is thin. The magnetic field is scattered and weak. The radiation reaches the ground. It would reach any human standing there. It would slowly, quietly, accumulate in the cells of their body. What it would do over a lifetime, we honestly do not know. This not knowing is part of the calm we are cultivating tonight. It is not a failure. It is not a reason to stop wondering. It is just a fact, like the distance to the planet or the color of its sky. The radiation on Mars is higher than on Earth. The long-term effects are uncertain. Any plan to live there must reckon with this, and as of now, no plan has fully solved it. The question remains open, and open questions, as we have said before, are allowed to exist. They are allowed to rest in the mind, unpressured and undemanding. You do not need to solve the radiation problem tonight. You do not need to design a shield. You can just let the knowledge sit there quietly, alongside the image of the red planet turning under its tan sky, bathed in the invisible rain from space, waiting for someone to figure out how to stay. The red planet turns under its tan sky, bathed in the invisible rain from space, waiting. And now we come to something that sits at the very center of any dream of living there. Water. Without water, there is no life as we know it. No drinking, no growing food, no making oxygen, no functioning human body. Every plan for a human future on Mars, whether it is a small research outpost or a larger settlement, depends on one thing above all others: finding water, using water, living with water. So the question is simple: is there water on Mars? And if so, where is it? What form is it in? And how hard would it be to reach? The first and most direct answer is this: there is no liquid water on the surface of Mars today. No rivers, no lakes, no oceans. If you stood on the surface and looked around, you would see no pools of water, no streams trickling through the rocks, no rain falling from the tan sky. The surface of Mars is dry. Dry as a desert, far drier than any desert on Earth. Dry as old bone. This is not because Mars never had water. It is because the conditions on the surface today will not allow liquid water to exist for any length of time. Remember what we said about the air pressure on Mars. It is less than 1% of Earth's. That means the boiling point of water is very different there. On Earth, at sea level, water boils at 100 degrees Celsius. We are used to that. We see pots of water bubble on the stove, and we know that is the point where liquid turns to gas. But on Mars, the air pressure is so low that liquid water exposed to the open air would boil instantly, even at temperatures near freezing. It would not be hot, it would just vaporize, turn to gas, and drift away into the thin atmosphere. So any water that might briefly appear on the surface, perhaps from a seep or a melt, would not last. It would fizz away into the air like a forgotten whisper. But that does not mean Mars is entirely dry. It means the water is hidden. It is frozen. It is underground. It is locked away in forms that require work to reach. And the most visible, most dramatic store of water on Mars is at the poles. The polar ice caps. These are vast sheets of ice that sit at the north and south ends of the planet. They grow and shrink with the seasons, just as the polar caps on Earth do, but they are made of more than just water ice. The Martian polar caps are a layered mixture of water ice and frozen carbon dioxide. Carbon dioxide, the main gas in the Martian air, freezes solid at the low temperatures found at the poles. So the caps are like a layer cake, with alternating bands of water ice and carbon dioxide ice, built up over thousands of years. The water ice in the polar caps represents an enormous amount of water. If all of it were melted, which is not a practical thing to do but helps us understand the scale, it would be enough to cover the entire planet in a layer of liquid water many meters deep. The water is there. It is just frozen solid, locked in the deep freeze of the polar regions. The poles, however, are not the most practical place for a human settlement. They are extremely cold, even by Martian standards. They experience months of darkness in winter. They are far from the milder equatorial regions where most mission plans focus. So the question becomes, is there water anywhere else? Somewhere closer to the middle of the planet, where temperatures are slightly less punishing and sunlight is more available? The answer, from data gathered by orbiting spacecraft over the past 2 decades, is yes. Water ice exists just beneath the surface in many mid-latitude regions of Mars, far from the poles. Instruments on orbiters have used radar to peer beneath the surface, sending down pulses of radio waves and listening for the reflections. Those reflections reveal layers of ice, sometimes just a few meters down, buried under a blanket of dry soil and dust. In some places, the ice is so close to the surface that it has even been exposed by the scoop of a lander. The Phoenix lander, which touched down near the North Polar region in 2008, dug a trench with its robotic arm and uncovered bright white material beneath the dust. That material was water ice. It sublimated, meaning it turned directly from solid to gas, over the course of a few days once it was exposed to the thin air. But it was there, real, confirmed, touchable water ice, just below the surface. These subsurface ice deposits are a critical discovery. They mean that future explorers might not have to travel all the way to the poles to find water. They might be able to land in a mid-latitude region where the temperatures are a bit more moderate and the sunlight is stronger, and still have access to water by digging down a few meters. The ice could be melted, purified, and used for drinking. It could be split apart into hydrogen and oxygen, using electricity to make breathable air and rocket fuel. It could be used to water plants in a greenhouse. Water is not just for drinking. It is a raw material, a building block for all sorts of life support systems. Finding accessible ice near the surface is one of the most encouraging things the orbiters have given us. But the water story of Mars goes deeper than the present. There is strong evidence that Mars was once a much wetter world. Billions of years ago, in its distant past, Mars had rivers. it had lakes. It may even have had a large ocean covering much of its northern hemisphere. The evidence for this ancient water is written all over the surface. Orbital images show dried river channels, winding across the landscape like the veins on a leaf. They show floodplains, where water once rushed across the ground in great volumes. They show the remains of ancient lakebeds, smooth, flat areas surrounded by the telltale shapes of old shorelines. The rovers have found minerals that can only form in the presence of liquid water, clays, sulfates, hematite, which on Earth is often deposited in hot springs or standing bodies of water. These minerals are not just surface stains, they are embedded in the rocks, and the rovers have drilled into them and analyzed them with their onboard laboratories. The picture that emerges is a world transformed. 4 billion years ago, give or take, Mars was warmer and wetter. Its atmosphere was thicker. It had a magnetic field to protect it. Water flowed freely across its surface, pooling in craters, cutting valleys through the highlands, emptying into a possible northern ocean. It was not Earth. It was never a twin of Earth. But it was a place where water, liquid water, was a normal part of the landscape. And then, over hundreds of millions of years, things changed. The core cooled, the magnetic field weakened, the atmosphere was slowly stripped away by the solar wind. The planet chilled. The water froze or evaporated or retreated underground. The rivers stopped. The lakes dried up. The ocean, if it existed, vanished. Mars became the dry, cold desert we see today. What happened to all that water? Some of it was lost to space. As the atmosphere thinned, water vapor in the upper atmosphere was broken apart by ultraviolet light from the sun. The hydrogen atoms, being very light, escaped into space. The oxygen atoms combined with rocks and stayed behind. Over billions of years, a significant amount of water was lost this way. Some of it remains frozen at the poles and in the subsurface ice we detect today. And some of it may still be liquid, deep underground. This last possibility is one of the open questions in Martian science. Could there be liquid water today, trapped in deep aquifers, miles below the surface, where the pressure from the overlying rock is high enough to keep it from boiling away? We do not know. There are some hints. Seasonal dark streaks appear on some slopes during warmer months, and one possible explanation is that they are caused by very salty liquid water briefly seeping to the surface. But these are not confirmed. Other explanations, involving dust or dry flows, are possible. The question of whether liquid water exists today, even briefly, in deep underground pockets, is still debated among scientists. It is not a settled matter. It is a quiet, unresolved question, and it is okay to let it remain unresolved. What matters for our purposes, for the question of living on Mars, is that water in usable forms is there. It is frozen, it is buried. It requires energy and equipment to extract, but it is there. The ice at the poles, the ice just beneath the mid-latitude soil, the water molecules locked inside certain minerals, which could be baked out with enough heat. These are real resources, mapped and measured. They are not abundant in an easy, convenient way. Nothing on Mars is easy or convenient, but they are present, and that presence changes the calculus of human settlement from impossible to merely extraordinarily difficult. Think about what water means to a human body. You are lying there, in the dark, and your own body is about 60% water. Every cell in you is a little bag of salty liquid. Your blood is mostly water. Your brain floats in a cushion of water. You lose water with every breath, every bead of sweat, every trip to the bathroom. On Earth, replacing that water is simple. You turn a tap or open a bottle, and there it is. Clean, liquid, abundant. On Mars, every drop of water would have to come from somewhere. Either you bring it with you from Earth, which is heavy and expensive and limits how long you can stay, or you extract it from the Martian environment. That extraction is a process. You have to mine the ice, you have to melt it, you have to filter it, purify it, test it for contaminants. You have to recycle it, capturing the water vapor from your breath and your sweat and your waste, cleaning it, and putting it back into the system. Nothing is wasted. Nothing is thrown away. The water loop must be closed and tight, because every molecule of water lost is a molecule that must be replaced by hard work. This is not a new idea. Space stations have been recycling water for decades. The International Space Station recycles urine and sweat and condensation into drinkable water. The technology exists, but on Mars, it would have to work reliably for years, without resupply from Earth, without a quick fix if something breaks. The water system would be one of the most critical pieces of any settlement. If it fails, people die. It is that simple. So the engineering must be robust. It must be redundant. It must be tested and tested again, and all of that testing has to happen before anyone goes, because once you are there, you are on your own. Picture now a future habitat on Mars, a small warm bubble of light in the vast cold desert. Inside, there is a greenhouse where plants grow under artificial lights. Their roots are in treated soil or nutrient solution, and they are watered with melted ice from the nearby deposit. The same water, after it cycles through the plants and the air, is captured, filtered, and used again. The people inside drink the same water that was, a week before, part of a tomato plant, or part of their own breath, or part of the ice that had sat frozen under the red dirt for millions of years. It is a closed circle, a tiny imitation of the water cycle that happens naturally on Earth. But on Earth, the cycle is vast and automatic. Rain falls, rivers flow, groundwater seeps, oceans evaporate. We do not have to manage any of it. On Mars, every step of the cycle must be managed by human hands and human machines. It is a different kind of relationship with water, not one of abundance, but one of careful, deliberate stewardship. Let this sink in as you lie here. You are warm and comfortable, and water is so easy for you that you do not even think about it. That is a gift of this planet, a gift of the thick atmosphere and the strong magnetic field and the billions of years of life that have shaped the world we know. On Mars, water is not a given. It is a treasure, buried and frozen, waiting to be coaxed out of the ground. It is a link to an ancient past, when rivers ran and lakes shimmered under a thicker sky. And it is a key to any possible future, the one thing that any human settlement absolutely must have. The water is there, it is real, it is reachable, but it will not come easily, and that quiet fact, like so many others tonight, is just part of the picture. It does not need to be solved, it just needs to be known. So let the image of frozen water beneath red soil rest in your mind. Let the image of ancient rivers, long dry, winding across an empty landscape, join it. The planet waits, holding its water close, keeping it locked in ice and buried in darkness. It has held it for billions of years. It will hold it for billions more. And one day, perhaps, human hands will reach down and touch it, and melt it, and drink it, and the cycle will begin again, in a small, warm bubble under a tan sky, on a world that was once wet and now is not. The planet waits, holding its water close, and the cycle will begin again, in a small, warm bubble under a tan sky. But water alone is not enough. To live, truly live, humans need more than something to drink. We need food to eat. We need air to breathe. We need the very basics of life, the things that on Earth are provided by the living world around us without a second thought. On Mars, none of that is provided. Nothing grows on its own. Nothing makes oxygen on its own. Every single thing a human body needs must either be brought from Earth or made from the raw materials of Mars itself. And so we come to the question of growing something from nothing. Can you take the red dirt of Mars, the thin carbon dioxide air, the frozen water, and turn them into a tomato? Into a breath of oxygen? Into a living system that can sustain itself? Let us start with the ground beneath your feet. On Earth, we call it soil. Soil is not just crushed rock. It is a living thing, a complex community of minerals and organic matter, and billions of tiny organisms. Dead leaves, decomposed roots, worm castings, fungal threads, bacteria. All of these are woven together into a dark, crumbly substance that holds water and nutrients and makes plant life possible. Soil is the skin of the earth, and it is the reason we can drop a seed into the ground and watch it grow. On Mars, there is no soil in this sense. There is only a layer of loose, dry, crushed rock that covers the surface. Scientists call this regolith. It is a word that simply means the broken-up rocky material that sits on top of solid bedrock. The Moon has regolith, asteroids have regolith, and Mars has regolith. The Martian regolith is not like Earth soil. It lacks the organic material, the decomposed, once-living stuff that gives Earth soil its richness. It is sterile, as far as we know. It contains no humus, no compost, no community of helpful microbes, and it has another problem. It contains toxic compounds called perchlorates. Perchlorates are salts that contain chlorine and oxygen. They are found in many places on Earth too, but they are particularly widespread in the Martian regolith. If a human were to handle raw Martian regolith without protection, the perchlorates could cause harm. They can interfere with the thyroid gland in the human body. They can contaminate water supplies. If you tried to grow a plant directly in untreated Martian regolith, the perchlorates would likely damage or kill the plant before it could produce anything edible. So the first step in growing food on Mars is not planting seeds. It is treating the regolith. You have to wash out the perchlorates, or use chemical processes to break them down, or simply bypass the regolith entirely and grow plants in water-based systems that do not use solid material at all. All of these are possible. They have been tested, in small ways, here on Earth. Researchers have taken simulated Martian regolith, made from crushed volcanic rock that matches the known composition of the Martian surface, and tried to grow plants in it. The results show that with enough treatment, with the addition of organic matter and nutrients and the removal of harmful compounds, plants can grow. The European Space Agency and other research groups have done experiments of this kind. They have grown small crops like tomatoes and rye and cress in simulated Martian soil. The plants were not as robust as plants grown in good Earth soil, but they grew. They produced edible material. The basic biology works. The problem is not that Martian regolith is impossible to farm. The problem is that it requires a great deal of work to turn it into something farmable. And even after treatment, you would not simply plow a field and scatter seeds under the open sky. The open sky of Mars, as we have talked about, is a near vacuum with no breathable oxygen and too much ultraviolet radiation and temperatures that plunge far below freezing every night. A plant placed outside on Mars would die in minutes. It would freeze, or suffocate, or have its cells burst from the low pressure. So any farming on Mars would have to happen inside sealed, pressurized, temperature-controlled greenhouses. These greenhouses would be bubbles of Earth-like conditions, filled with thick, warm air and lit by either the dim natural sunlight or by powerful artificial lights. They would be more like indoor vertical farms on Earth than like the open wheat fields we picture in the countryside. Every plant would be precious. Every square meter of growing space would be carefully managed. There would be no weeds, no pests, no birds, no bees. Pollination, if the plants needed it, would have to be done by hand or by small machines. The entire ecosystem of a farm, the soil microbes, the pollinators, the natural rain, the gentle wind, all of it would have to be replaced by human engineering. This is not a small undertaking. A greenhouse capable of feeding even a small crew for an extended period would need to be large, well-lit, and supplied with water and nutrients. The energy demands would be significant. The water loop would have to be tight, capturing every drop of moisture that evaporates from the leaves and the soil, and recycling it back. The nutrients, like nitrogen and phosphorus and potassium, would have to come from somewhere. Some could be brought from Earth. Some might be extracted from the Martian regolith itself, which contains many of the mineral elements plants need once the toxic compounds are removed. Some could be recycled from human waste, a closed-loop system where nothing is thrown away. This is the reality of growing food on another world. It is not romantic. It is not a pastoral vision of red fields turning green. It is an industrial process, a careful and deliberate act of creation, a fight against the natural state of the planet. Now let us turn to the other thing we need. Air. Breathable air. On Earth, the oxygen we breathe comes from plants and from tiny organisms in the ocean called phytoplankton. They take in carbon dioxide and, using the energy of sunlight, split it apart and release oxygen as a waste product. This process, photosynthesis, is the great engine that has filled Earth's atmosphere with oxygen over billions of years. On Mars, the atmosphere is already mostly carbon dioxide. That is the raw material. Could we use that carbon dioxide to make oxygen, not with plants but with a machine? The answer is yes. It has already been done on a small scale on the surface of Mars itself. In the year 2021, the Perseverance rover landed on Mars carrying a small instrument called MOXIE. That name is an acronym. It stands for Mars Oxygen In Situ Resource Utilization Experiment. The key phrase there is in situ resource utilization, which simply means using the local materials, the stuff that is already there, instead of bringing everything from Earth. MOXIE was designed to test whether a machine could pull carbon dioxide from the Martian air, heat it up, and use electricity to split the carbon dioxide molecules into carbon monoxide and oxygen. The oxygen would be a useful product. The carbon monoxide would be vented back out as waste. And MOXIE worked. Over the course of several test runs, spread out across different seasons and different times of day, MOXIE successfully produced small amounts of pure oxygen from the Martian atmosphere. The amounts were very small, a few grams per hour. That is not enough to keep a person alive. It is a tiny fraction of what would be needed. But the point was not to produce useful amounts of oxygen yet. The point was to prove that the chemistry works, that the technology can function in the real Martian environment, with real Martian air, real Martian dust, real Martian temperatures. And it did work. It proved that the principle is sound. A larger version of MOXIE, scaled up enormously, could theoretically produce enough oxygen to serve two purposes. First, to provide breathable air for a human crew. Second, and in fact the larger need, to serve as the oxidizer for a rocket engine, the part that allows the fuel to burn. A rocket that lands on Mars and then wants to take off again to come home needs a huge amount of oxygen. Bringing that oxygen from Earth would make the mission vastly heavier and more expensive. Making it on Mars, from the air itself, is one of the most important technologies for any long-term human presence. So we have the beginnings of an answer. Food can be grown, but not easily, and not outside. Oxygen can be made, but it requires machines and energy. Both of these processes are real. They have been tested. They are not science fiction. But they are also not yet ready for the demands of a real human mission. Scaling up from a small experiment like MOXIE to a system that can support a crew of 4 or 6 or 8 people for months and years is an enormous engineering challenge. Scaling up from a few experimental tomato plants in simulated regolith to a greenhouse that can reliably feed a settlement is an equally enormous challenge. These are not problems of basic science. The basic science is known. These are problems of engineering, of reliability, of energy supply, of building systems that do not fail, because if they fail, people die. Think about the energy question for a moment. Splitting carbon dioxide to make oxygen takes electricity. Running powerful lights for a greenhouse takes electricity. Melting ice to make water takes electricity. Heating a habitat against the deep cold of the Martian night takes electricity. Where does all that electricity come from? Solar panels are the most obvious answer. They work on Mars. Rovers have used them for decades. But Mars gets only about half as much sunlight as Earth, so solar panels produce less power than they would here. Dust storms can blot out the sun for weeks or months at a time, coating the panels in fine red powder and cutting their output to nearly nothing. Any settlement that relies on solar power would need large battery banks to store energy through the dark spells, or backup generators of some other kind. Small nuclear power sources, like the one that powers the Perseverance rover and previously the Curiosity rover, are another option. These devices use the heat from a small amount of radioactive material to generate electricity. They are reliable and long-lasting and do not care about dust storms. But they produce only a limited amount of power. Scaling them up to the level needed for a human habitat, with all its life support and food production and water processing, would require a much larger nuclear reactor, and that brings its own set of technical and safety challenges. The energy problem is another one of those open, unresolved questions, not unsolvable in theory, but unsolved in practice. Let all of this settle gently. The Martian regolith, dusty and toxic, waiting to be washed and fed and turned into something that can support a seed. The thin carbon dioxide air, waiting to be pulled into a machine and split apart into breathable oxygen. The dim sunlight, or the quiet heat of a nuclear source, waiting to power it all. Growing something from nothing on Mars is not a matter of scattering seeds and waiting for rain. It is a matter of building, from scratch, the entire support system that Earth provides for free. It is a matter of creating a tiny, artificial version of our own living world, sealed inside a bubble, clinging to the edge of a planet that does not care whether it works or not. And yet, the fact that it is possible at all is remarkable. The same chemistry that works on Earth works on Mars. A plant seed, given the right conditions, does not know what planet it is on. It just grows. A carbon dioxide molecule, given enough electricity, splits apart just the same on Mars as it does in a laboratory on Earth. The laws of physics and chemistry are the same everywhere. The challenge is not that Mars makes these things impossible. The challenge is that Mars makes them hard, very hard. Harder than anything we have had to do in space so far. As you lie here, with your breathing slow and your body heavy, you can let the image of a Martian greenhouse float into your mind. A warm, humid, brightly lit space, filled with green leaves and the smell of damp earth. Outside, the tan sky and the frozen ground and the thin wind. Inside, a small piece of earth, carefully tended, quietly growing. Tomatoes ripening under artificial lights. Lettuce leaves unfurling in nutrient-rich water. A machine in the corner humming softly, pulling in the thin Martian air and puffing out a steady trickle of oxygen. This is the dream. And it is not an impossible dream. It is just a difficult one. A dream that will take decades of work to make real. But the work has begun. The seeds have been tested. The machine has run. The path is known. What remains is the long, patient labor of making it ready for human life. And that labor, like the planet itself, is in no rush. It can wait. It can unfold slowly, over years and decades, while the red world turns quietly under its tan sky. The red world turns quietly under its tan sky, and the long, patient labor of making it ready for human life unfolds slowly. Now we come to a question that follows directly from everything we have talked about so far. If the surface of Mars is so hostile, if the air is too thin, and the radiation is too high, and the temperature swings are so extreme, where would anyone actually live? What would a Martian home look like? Not a temporary campsite, not a flag planted for a few days before heading home, but a place where people could stay for months or years. The answer, in almost every serious proposal put forward by engineers and scientists, is that people would not live on the surface of Mars. They would live under it, or inside it, surrounded by thick walls of rock or soil or ice. The surface would be a place to visit, to work, to explore, but the place you would sleep, eat, and spend most of your time would be a shelter, buried and protected. The reasons for this go back to the dangers we have already discussed. Radiation is the biggest one. The thin atmosphere and the lack of a global magnetic field mean that the surface of Mars is constantly exposed to cosmic radiation and solar radiation. Short visits to the surface, lasting a few hours or a day, would not deliver a dangerous dose. But over weeks and months and years, the dose accumulates. The only practical way to reduce that exposure is to put mass between the human body and the sky. Thick layers of material that can absorb or deflect the incoming particles before they reach living tissue. On Earth, our atmosphere does this job for us, and it is equivalent to a layer of shielding several meters thick. On Mars, we would have to build that shielding ourselves. The simplest form of shielding is dirt, Martian soil. The same dusty regolith we talked about in the context of farming is heavy and plentiful. If you pile enough of it on top of a habitat, you create a barrier that radiation has to struggle through. Studies suggest that a layer of Martian soil about 1 to 3 meters thick would reduce the radiation dose inside a habitat to levels much closer to what we experience on Earth. Not exactly the same, but much safer for long-term living. You would not need to import this material from Earth. You would just scoop it up from the ground around you, using bulldozers or excavators, and pile it on top of your living quarters. The weight of the soil would also help with another problem, the pressure difference. The habitat inside is pressurized to Earth-like levels, while the outside is near vacuum. The walls have to be strong enough to hold that pressure in. A thick layer of soil on top adds structural support, helping the walls resist the outward push of the air inside. This idea, covering habitats with local soil, is sometimes called regolith shielding. It is one of the most straightforward and widely agreed upon concepts in Martian settlement planning. But there are other ideas too. Mars has natural features that might serve as ready-made shelters. One of the most intriguing possibilities involves something called lava tubes. A lava tube is a natural tunnel formed by flowing lava. When a volcano erupts and sends rivers of molten rock across the surface, the outer layer of the lava flow can cool and harden while the inside remains liquid and keeps moving. Eventually, the liquid lava drains away, leaving behind an empty tunnel, a long cave with walls of solid rock. Lava tubes exist on Earth. They exist on the Moon, and orbital images have identified features on Mars that look very much like lava tubes, particularly on the slopes of the giant volcanoes in the Tharsis region. A Martian lava tube would be an extraordinary find for a human settlement. The rock ceiling above the tube would provide natural radiation shielding, potentially many meters thick, without any digging or piling required. The interior would be protected from the temperature swings of the surface, maintaining a more stable environment. The entrance could be sealed and pressurized, creating a vast, habitable space, with room for living quarters, laboratories, greenhouses, and storage. Some lava tubes on Mars appear to be very large, tens of meters wide and hundreds of meters long. They could potentially house entire communities. The main challenge is that we do not yet know enough about them. We have not explored any Martian lava tube up close. We do not know how stable their ceilings are, or whether they are blocked by debris, or whether they contain any hazards we have not anticipated. They are a tantalizing possibility, but they remain just that, a possibility. Another idea is to build with ice. In regions where water ice is abundant just below the surface, a habitat could be constructed with walls made largely of ice. Ice is surprisingly good at blocking certain types of radiation. It is also, in a sense, a building material that can be shaped and melted and refrozen, and it has the added benefit of being transparent, at least partially, so some natural light might filter through. Imagine a domed structure, its walls thick with frozen water, glowing faintly from the sunlight outside. The ice would protect the inhabitants while also serving as a visible reminder of the water that makes life possible. This idea has been studied on paper, but like so many concepts for Mars, it has not been tested in the real environment. Beyond the natural caves and the ice domes, there is another approach that has gained attention in recent years: three-dimensional printing. The idea is to send ahead a robotic construction machine that would scoop up Martian regolith, process it, and print it layer by layer into solid walls. This is similar to how some houses are now being three-dimensionally printed on Earth, using concrete or other materials. The advantage is that you do not need to bring building materials from Earth. You use the local dirt, which is everywhere, and you print a structure that is precisely designed for the conditions. The walls could be thick enough to provide radiation shielding and strong enough to hold pressure. The printer itself would be the only piece of equipment that needs to come from Earth. Once it arrives, it could work autonomously for months, building the habitat before the first human crew ever launches. By the time the astronauts arrive, their home would be waiting for them, already tested and ready. This idea has been the subject of research by NASA and other space agencies. Small-scale tests have been done on Earth, printing structures out of simulated Martian material. The technology is real and advancing, but scaling it up to a full habitat and making it reliable enough to trust with human lives is a different matter. The printer would have to operate in the Martian environment, with its fine dust and extreme temperatures and low gravity. It would have to function without repair or human intervention for long periods. These are not impossible challenges, but they are not yet solved. They are part of the long, patient labor we spoke of, the work of turning concepts into reality. What all of these ideas have in common is a recognition that the surface of Mars is not a place to linger unprotected. The romantic image of a human standing on a ridge, looking out at the red plains under an open sky, is a moment. It is a brief and precious moment, but it is not where the living happens. The living happens inside, underground, or under a thick blanket of soil, or deep within a lava tube, or inside a printed shell. The windows, if there are any, would be small and heavily shielded. The lighting would be artificial, tuned to the rhythms of the human body. The air would be recycled. The water would be recycled. The temperature would be steady and warm. It would be, in many ways, a life not so different from living in a sealed base in Antarctica or aboard a submarine deep under the ocean. A life of controlled environments and careful routines. A life where the outside is always present, but always held at a distance. Picture such a habitat now. A series of connected modules half buried in the red soil, with a thick layer of regolith piled over the top. The entrance is an airlock, a heavy door that seals tight and cycles the pressure when someone comes or goes. Inside, the lights are warm, tuned to a soft yellowish white that feels like a late afternoon on Earth. The walls are lined with panels of equipment, humming quietly. There is a small galley where food is prepared, a table where people gather to eat, narrow corridors leading to private sleeping quarters. In one module there is a greenhouse, bright with pinkish grow lights, the air thick with the smell of damp soil and tomato leaves. In another module, there is a small medical bay and an exercise area, because the low gravity demands constant work to keep the body strong. Through a small, thick window, you can see the tan sky and the red ground, but the view is distant, framed, and contained. The real world, the human world, is the one inside. This is not a vision of deprivation. It is a vision of careful, deliberate design. Every square meter of space would be precious. Every system would have a backup. Every routine would be thought through. The people living there would not be roughing it in the wilderness. They would be living inside a complex machine, one that keeps them alive in an environment that does not want them. And they would know that machine intimately. They would maintain it and repair it and understand its workings, because their lives would depend on it. This is a different kind of relationship to home than most of us have. Our homes on Earth are places of rest and refuge, but we do not have to constantly monitor the air quality, or the pressure seals, or the radiation levels. On Mars, those things would be as natural as checking the weather, because the weather, in a sense, is inside the walls as much as outside them. Let the image of that buried habitat rest in your mind, the quiet hum of the life support systems, the soft glow of the lights, the thick layer of red soil overhead, blocking the radiation, holding the cold at bay. Outside, the tan sky and the frozen plains. Inside, a small pocket of Earth, warm and green and alive. This is the realistic dream of living on Mars. Not a city of gleaming domes on the open surface, not a terraformed paradise with blue skies and flowing rivers. Those are fantasies for the far future, if they are possible at all. The realistic dream is a shelter, dug in and covered over, a place of safety and care and quiet, a place where human life could persist, not by conquering the environment, but by protecting itself from it, patiently and persistently, one soul after another. And this dream, like all the others we have talked about tonight, is not yet real. No lava tube has been explored, no Martian habitat has been printed, no pile of regolith has been laid over a pressurized module on the surface of Mars. These are drawings on paper, computer models, small tests in laboratories on Earth. They are serious ideas, grounded in real science and real engineering. But they are not built, they are not proven. They are part of the long arc of work that lies between us and any human future on the fourth planet. That arc stretches out ahead of us, unbroken and patient. It does not demand to be finished tonight. It just waits, like the planet itself, turning quietly under its tan sky, while the people who dream of going there continue to think and plan and test and build. The work continues. The question remains open. And somewhere, in a laboratory or a design studio or a dusty field test, the first piece of a Martian home is being imagined into existence, one careful step at a time. The work continues, and the question remains open. And somewhere, the first piece of a Martian home is being imagined into existence. Now we must turn our attention inward, to the bodies that would live in those homes. Not the engineering of habitats, not the chemistry of oxygen production, not the geology of water ice, the human body itself, the heart, the bones, the muscles, the blood, the intricate systems that evolved over millions of years in the steady embrace of Earth's gravity. What happens to that body when it leaves the Earth behind? What happens when it arrives on a world where the pull of gravity is only a fraction of what it was built for? We have talked before about the gravity of Mars. It is about 38% of Earth's gravity. If you weigh 100 pounds here, you would weigh 38 pounds there. Every step you take would feel lighter. Every object you lift would feel easier. At first, this sounds pleasant, a relief from the constant downward pull, a chance to move with a grace and ease that is not possible on Earth. And in the short term, it would be pleasant. The Apollo astronauts on the Moon, where gravity is only about 1/6 of Earth's, described the experience of walking and jumping in low gravity as joyful, a kind of floating bounce that felt natural and fun. But they were there for only a few days. The question we are asking is about months and years, about living a whole life, or a large part of a life, in that reduced gravity. And the honest answer is that we do not know what that would do to a human body. We genuinely, deeply do not know. What we do know comes from studying astronauts who have spent long periods in an even more extreme environment. The International Space Station. In orbit around Earth, the astronauts aboard the station experience what is called microgravity. They are not beyond Earth's gravity entirely. The pull of the Earth still reaches them, which is why the station stays in orbit rather than flying off into space. But because they are in free fall, constantly falling around the curve of the planet, they experience a state of near weightlessness. Their bodies float. Their muscles do not have to work to hold them upright. Their bones do not have to bear weight, and over time, this lack of loading causes changes. The changes are well documented. Muscles weaken. Without the constant work of fighting gravity, muscle fibers shrink. The muscles of the legs and the back and the core, the ones we use all day, every day, just to stand and walk and sit up straight, begin to waste away. Astronauts on the station follow a strict exercise routine, 2 hours a day or more, using specialized machines like treadmills with harnesses that pull them down and resistance devices that simulate weightlifting. These routines help. They slow the muscle loss significantly, but even with exercise, some loss still occurs. The body is not fully fooled by the exercise machines. It knows, at some deep level, that the constant downward load is missing. Bones change too. On Earth, our bones are constantly being remodeled. Old bone material is broken down by the body, and new bone material is laid down. The rate of breakdown and buildup is balanced by the mechanical stresses we place on our skeletons. When you walk, when you run, when you lift something heavy, you send signals to your bones that they need to stay strong. In microgravity, those signals are dramatically reduced. The body responds by slowing down the buildup of new bone, while the breakdown continues at its normal pace. The result is a net loss of bone density. Over months in orbit, astronauts can lose bone mass at a rate similar to someone with osteoporosis on Earth, a disease that makes bones fragile and prone to breaking. The loss is not uniform. It affects the weight-bearing bones most heavily, the hips and the spine and the legs. Exercise helps with this too, but again, it does not completely stop the loss. There are other changes as well. Fluids in the body shift upward because gravity is not pulling them down into the legs and feet. Faces puff up, sinuses feel congested. The sense of balance, which relies on tiny organs in the inner ear that detect gravity, gets confused. Astronauts often feel dizzy or nauseous for the first few days in space, a condition called space adaptation syndrome. Their sense of taste can change. Their sleep can be disrupted. The very shape of the eye can be affected, with some astronauts developing vision problems due to changes in the pressure and shape of the eyeball and the optic nerve. All of these are being studied. All of them tell us that the human body is exquisitely tuned to one gravity, the gravity of Earth, and when you take that away, the body notices. Now, the key point is this. All of these studies have been done in microgravity, the near weightlessness of orbit. Mars has gravity. It is reduced, but it is not zero. 38% of Earth's gravity is still a significant pull. It is enough that water flows downhill. Enough that dust settles to the ground. Enough that a dropped object falls, not floats. The human body on Mars would not be adrift. It would be planted on the ground, bearing weight, working against resistance. The question is whether 38% is enough to prevent the slow deterioration we see in orbit. It might be. We have reason to hope that it might be, but we do not have proof. No human has ever lived in partial gravity for an extended period. The only data we have from partial gravity comes from the Apollo missions on the Moon, which lasted only a few days each. That is not enough time to measure bone density changes or muscle wasting. It is barely enough time to get a sense of how it feels to walk and work. The longest stay on the Moon was the Apollo 17 mission, which lasted about 3 days on the surface. 3 days tells us nothing about what happens over 3 years, or 30 years. There have been proposals to build a centrifuge on the International Space Station, a spinning chamber that would create artificial gravity for mice or other small animals, to study the effects of partial gravity over multiple generations. Some of these experiments have been planned, but they have not yet been carried out on the scale needed to give us clear answers. We are operating, as we so often are with Mars, in a state of informed uncertainty. Scientists openly acknowledge this as a real gap in knowledge. It is not a gap that can be filled by theory alone. We can model what we think might happen, based on what we know about biology and physics. But biology is full of surprises. The body adapts in ways that are not always predictable. Perhaps the threshold for healthy function is very low, and 38% is more than enough to keep bones strong and muscles firm. Perhaps the threshold is higher, and even Mars' gravity will cause slow, cumulative damage over a lifetime. Perhaps some systems, like the cardiovascular system or the balance organs, are more sensitive than others. Perhaps children born on Mars who have never known Earth's gravity would develop differently, with longer, lighter bones and different patterns of muscle attachment. We do not know. Think about what this means for the question we are sitting with tonight. Could humans ever live on Mars? Not just visit, not just plant a flag and take some photographs and fly home. Live, spend a lifetime there, raise children there, grow old there. The answer to that question depends, in large part, on the biology of gravity. If the human body can adapt to 38% gravity without serious long-term harm, then the door is open. Not easy, but open. If the human body slowly degrades over years in partial gravity, no matter how much exercise is done, then living on Mars permanently may be a much harder proposition. It may require rotating habitats that spin to create artificial gravity, which is a far more complex engineering challenge. Or it may require accepting that Martians would never be able to return to Earth, their bodies too weakened to withstand the crushing pull of the home planet. Or it may mean that Mars is a place for short stays, for research tours of a year or two, not for building a second human world. These are not questions with answers yet. They are questions that only going there and staying there can answer, and that, in itself, is a sobering thought. The first people who travel to Mars will be, in a very real sense, test subjects. They will be the first to discover what partial gravity does to the human body over months and years. They will have exercise routines and monitoring equipment and medical protocols, all designed to track changes and slow damage. But the ultimate outcome is unknown. They will be pioneers not just of a place, but of a physiological frontier, exploring the limits of the body as much as the landscape. Consider also the journey itself. We mentioned earlier that the trip to Mars takes 7 to 9 months with current rockets. That is 7 to 9 months in the microgravity of interplanetary space, floating in a small metal can, with no gravity to pull the body down. By the time the astronauts arrive at Mars, they will already have experienced significant muscle and bone loss from the journey. They will step onto the surface lighter and weaker than when they left Earth. The Martian gravity will feel like a relief after weightlessness, but it will also be a challenge. They will have to rebuild their strength in a new, unfamiliar gravitational environment. The exercise countermeasures they used on the ship will have helped, but they will not have prevented all loss. The first days and weeks on Mars will be a time of physical readjustment, of sore muscles and uncertain balance, of learning to move all over again in a body that has forgotten what gravity feels like. And then, if they ever come back, they will have to go through it all in reverse. The journey home is another 7 to 9 months in microgravity, further weakening the body. Then, the sudden shock of Earth's full gravity, pulling them down, making every limb feel heavy, every heartbeat a labor. Astronauts returning from long stays on the International Space Station often need weeks or months to fully recover their Earth legs. Some changes, particularly in bone density, may never fully reverse. A round trip to Mars, with long stays in partial gravity at both ends and long stretches of weightlessness in between, is a physical ordeal unlike anything humans have ever attempted. It is not impossible. People have endured incredible physical challenges before. But it is a challenge, a serious and sobering one. Let all of this settle quietly. There is no need to reach a conclusion. The human body is a remarkable thing, adaptable and resilient, but it is not infinitely so. It has limits, and those limits were shaped by the very specific conditions of this planet. The pull of one gravity, the 24-hour day, the air we breathe, the food we eat, all of it is part of a system that our bodies are woven into. Taking the body out of that system and placing it into another one, a system with less gravity and different light and different air, is not a simple transplant. It is a deep and fundamental challenge to the biology that made us. Whether that challenge can be met over a lifetime is not known. The science is not there yet. The data is not there yet. The only way to get the answer is to go, and that going, when it happens, will be an act of trust. Trust in the machines that keep the air in and the radiation out. Trust in the exercise routines and the medical protocols. And trust in the body itself to find a way to live, truly live, on a world that pulls with less than half the strength of home. That going, when it happens, will be an act of trust. Trust in the machines, trust in the protocols, trust in the body itself. And now, before we drift toward the close of this long, quiet picture we have been painting together, it is worth grounding ourselves in something solid. Not in what might happen someday, not in what engineers have drawn on paper, but in what has actually been done, what has actually been sent, what real machines, built by real hands, have traveled across the distance and touched the surface of Mars and sent back their quiet reports. The story of Mars exploration is not a story of human footprints on red soil. Not yet. It is a story of robots. patient, clever, tough little machines that have crossed the void in our place, serving as our eyes and our hands and our ears. This story begins in earnest in the 1970s, when the first successful landers reached the surface. They were called Viking. Viking 1 and Viking 2. They were built by NASA, the American Space Agency, and they were ambitious for their time. Each Viking lander carried a suite of instruments designed to study the Martian soil and atmosphere, to take photographs of the landscape, and to perform a set of experiments that would test for signs of life. The results of those life detection experiments were mixed and puzzling. Some of the tests gave results that might, in isolation, suggest biological activity, but other tests, designed to confirm those results, came back negative. The scientific consensus that emerged was that the experiments had detected unusual chemical reactions in the soil, not living organisms. The Viking landers did not find life, but they did prove that landing on Mars and operating on its surface for extended periods was possible. They sent back the first photographs from the ground, showing a rocky, desert-like landscape under a pinkish sky. They measured the temperature and the wind. They gave us our first real, grounded sense of what Mars is like at the level of a human standing on it. The Viking landers were the pioneers, the first to touch down safely and stay. After Viking, there was a long gap. Budgets shifted, priorities changed. For a time, Mars went quiet. But in the 1990s, the exploration resumed with a new generation of machines. The Mars Pathfinder mission landed in 1997, carrying a small rover named Sojourner. Sojourner was tiny, about the size of a microwave oven. It rolled slowly across the surface, analyzing rocks and sending back data. It was a technology demonstration, a test to see if a rover could work on Mars, and it worked. It paved the way for larger, more ambitious rovers to come. The first of those larger rovers were Spirit and Opportunity. They landed in January of 2004, on opposite sides of the planet. They were designed to last for 90 Martian days, or sols. But they far outlasted their warranties. Spirit kept roving until 2010, when it became stuck in soft sand and could no longer move. It continued to operate as a stationary science platform for a while, before finally going silent. Opportunity kept going even longer. It rolled across the Meridiani Planum, a vast flat plain, studying rocks and craters and sand dunes. It survived dust storms and cold winters and the slow degradation of its parts. It kept communicating with Earth until 2018, when a planet-wide dust storm blotted out the sun and starved its solar panels of light. By the time the storm cleared, Opportunity had fallen silent. It had operated for more than 14 years, covering over 45 kilometers of Martian ground, a machine built to last 3 months, surviving for more than a decade and a half. That is the kind of overachievement that these missions have made routine. Then came Curiosity. Curiosity landed in 2012 in a crater called Gale, using a complicated sky crane system that lowered the rover gently to the ground on cables. Curiosity is much larger than Spirit and Opportunity. It is about the size of a small car. It carries a full laboratory inside its body, capable of drilling into rocks, scooping up soil, and analyzing the samples with sophisticated instruments. It has a laser that can zap rocks from a distance and read the light that comes back to determine their composition. It has the radiation detector we talked about earlier, the one that has measured the radiation environment on the surface directly. Curiosity's main goal has been to study the geology and climate of Mars, and to assess whether Gale Crater ever had conditions that could have supported microbial life. The data it has gathered suggests that, yes, Gale Crater once held a lake, a body of water that was not too acidic or too salty for life as we know it. The building blocks were there. The water was there. The energy sources were there. Curiosity has not found life. It was not designed to. But it has found that the ancient environment of Mars was habitable, at least in that one spot, at least for a time. And then, most recently, Perseverance. Perseverance landed in February of 2021 in a crater called Jezero. Jezero is a special place. Orbital images show that it once held a river delta where water flowed into a lake and deposited layers of sediment. On Earth, river deltas are excellent places to preserve signs of ancient life. Perseverance carries instruments to study the geology and climate of Jezero, just as Curiosity did at Gale, but it also has a very specific additional goal. It is collecting samples, small tubes of rock and soil, carefully sealed and left on the surface for a future mission to pick up and bring back to Earth. That future mission, called Mars Sample Return, is still in the planning stages. It is complicated and expensive, but if it succeeds, it will bring pieces of Mars back to our laboratories, where scientists can study them with tools far more powerful than anything we can send on a rover. Perseverance also carried MOXIE, the oxygen-making experiment we talked about earlier. And it carried a small helicopter named Ingenuity, a technology demonstration meant to test whether powered flight is possible in the thin Martian air. Ingenuity succeeded beyond all expectations, making dozens of flights, scouting ahead of the rover, and proving that the skies of Mars, thin as they are, can be navigated by a spinning rotor. These are the machines that have gone before us: Viking, Pathfinder and Sojourner, Spirit and Opportunity, Curiosity, Perseverance and Ingenuity. There have been orbiters as well, too many to name them all, circling the planet and mapping it in ever greater detail. There have been landers from other nations and attempts that did not succeed because landing on Mars is hard and failure is part of the process. But the machines that have succeeded have built a foundation of knowledge. They have given us the data we need to ask the questions we have been asking tonight: the temperature and the air pressure, the radiation levels and the soil chemistry, the presence of ancient water and the absence of present life. All of it comes from these robots, these patient extensions of human curiosity. And yet, for all of this, no human has ever set foot on Mars. Every photograph you have ever seen of the Martian surface was taken by a machine. Every rock that has been analyzed was analyzed by a robotic arm or a laser beam. Every measurement of the atmosphere was made by an instrument that no human hand has ever touched after it left Earth. All Mars exploration to date has been robotic. This is not a failure. It is a deliberate, careful, step-by-step approach. Robots are cheaper than humans. They do not need food or water or air. They do not get sick or lonely or bored. They can operate in environments that would kill a human in minutes. They are the scouts, the advance team, the ones who go first and make sure it is safe. The question of when humans will follow is a question that has been asked for decades. Various space agencies and private companies have stated long-term interest in crewed missions. NASA has talked about sending humans to Mars in the 2030s or 2040s. Private companies have made ambitious announcements about establishing colonies, but no firm agreed timeline exists. There is no launch date set in stone. There is no spacecraft built and waiting. There are plans and concepts and design studies and test programs, but there is no committed, funded, irreversible human mission to Mars. This may change. It probably will change at some point. But as of this quiet moment, as you lie here in the dark, the human presence on Mars is still a matter of what might be, not what is. This is not a pessimistic thing to say. It is just an honest thing to say. The machines have done extraordinary work. They have shown us that Mars is a real place, a specific place, with its own history and its own character. It is not a blank canvas for our fantasies. It is a world with its own rules and its own challenges. The machines have told us what those rules and challenges are. Now it is up to us, the humans, to decide whether and when to take the next step. That decision involves money and politics and international cooperation and 1,000 other factors that have nothing to do with the science. It involves risk and uncertainty and the willingness to accept that some things cannot be known until we go. So let the image of all those machines rest in your mind. The Viking landers, sitting quiet and still on the plains where they touched down in the 1970s, no longer transmitting, but still there, still intact, waiting for the day when human hands might come to visit them. Spirit, stuck in the sand, its solar panels coated with dust, silent now but a monument to a mission that lasted years longer than anyone expected. Opportunity, somewhere in the vastness of Meridiani Planum, its last message to Earth being, in essence, my batteries are low and it is getting dark. Curiosity, still roving, still drilling, still zapping rocks with its laser, climbing the slopes of Mount Sharp in Gale Crater. Perseverance, in Jezero, dropping its sealed sample tubes onto the surface, hoping that someone will come to collect them. Ingenuity, the little helicopter, resting on the sand after its final flight, having done what no aircraft had ever done before on another world. These are not just pieces of metal and circuits, they are ambassadors. They are the quiet, tireless representatives of a species that looked up at a red point of light and decided to reach for it. They have done their work. They are still doing it. And one day, perhaps, they will be joined by living, breathing humans who will stand beside them and look out at the same red plains and the same tan sky and feel, for the first time, the gravity of another world pulling gently at their bodies. That day is not here yet, but the machines are there, waiting, holding the door open. The machines are there, waiting, holding the door open. And now we have come to the end of this long, slow picture we have been painting together. Not an end in the sense of a conclusion, not a resolution or a final answer, just a gentle resting point, a place to let the images settle, a place to return to the beginning, to the small red point of light in the dark sky, and see it with all the layers we have added, one by one, quiet fact by quiet fact. If you were to step outside now, in your mind, and look up, you would see that same steady reddish dot. It has not changed. It has not moved from its place in the sky. All the facts we have talked about tonight, all the numbers and measurements and challenges and unknowns, do not alter the simple reality of that light. It glows just as it glowed for the Babylonians, for the Egyptians, for the Greeks and the Romans, and for every human who ever tilted their head back and wondered. It is still just a point of light, a wanderer among the fixed stars, a neighbor on the fourth ring from the sun. And the question we have been holding, the question of whether humans could ever live there, is still open. It was open when we began, and it is open now. We have not solved it tonight. We were never going to solve it tonight. That was never the purpose. The purpose was to sit with it, to turn it over gently, to feel its weight and its texture and its complexity, to understand that this is not a question with a simple yes or no. It is a question made of many smaller questions, each one of them layered and deep. The question of the air, so thin that it cannot hold warmth or moisture or life. The question of the water, frozen and buried and waiting. The question of the radiation, silent and invisible, accumulating in cells over time. The question of the gravity, gentle and strange, with effects on the body that we honestly do not yet understand. The question of how to grow food in toxic dirt, how to make oxygen from thin carbon dioxide, how to build a home that can shield against the cold and the radiation and the emptiness. The question of whether the human body and the human mind can endure the long journey, the long stay, the long return. All of these questions are open, all of them are being worked on, slowly and patiently, by people who have dedicated their lives to the asking, but none of them is fully answered. And that uncertainty is honest. It is not a disappointment. It is not a failure of science or imagination. It is simply the truth of where we are. We are a species that has learned to send small machines across millions of kilometers of empty space. We have learned to land them gently on another world and command them to turn their cameras and extend their arms and drill into rocks. That is extraordinary. That is something no other life on Earth, as far as we know, has ever done. But we have not yet learned how to send ourselves safely and keep ourselves alive and bring ourselves home, or stay there and build a life. That is a harder problem. It is a problem that may take decades more or longer to solve. And it is possible, we must say this plainly, that it will never be solved. It is possible that the challenges are too great, the costs too high, the risks too deep. It is possible that Mars will remain a place for robots, not for people. That is a real possibility, and it is okay to hold that possibility in the mind without fear or sadness. The universe does not owe us a second home. The fact that we have one, this beautiful blue and green world, is a gift beyond measure. But it is also possible, and equally honest to say, that humans will go. That someday, perhaps in the lifetime of a child already born, a ship will cross the distance, and a pair of boots will touch the red dust, and a human voice will speak into a radio, and the words will travel back across the void to waiting ears on Earth. That moment, if it comes, will not be the end of the story. It will be the beginning of a new set of questions, harder and deeper than the ones we have asked tonight. Questions about what it means to live on another world. Questions about how a Martian society would grow and change. Questions about what it would do to the human spirit to live under a tan sky, inside a buried shelter, knowing that the air outside is not enough, and the radiation is always falling, and the gravity is only a fraction of what your bones were built for. Those questions cannot be answered in advance. They can only be lived. So as you lie here, on the edge of sleep, let the image of Mars return to its simplest form. Not a list of challenges, not a destination with a timeline, not a problem to be solved, just a small red light in the dark sky. A planet that has existed for more than 4 billion years. A world that was once wet and warm, with rivers and lakes and maybe an ocean, and is now cold and dry and quiet. A world that spins on its axis at a tilt very close to our own, giving it seasons and weather and long, slow changes. A world with 2 tiny moons, Phobos and Deimos, circling close and fast, named for fear and panic, but being nothing of the sort. A world that has been visited by our machines, by Viking and spirit and opportunity and curiosity and perseverance, each one adding a few more pieces to the puzzle. A world that waits, patiently, as it has always waited, for whatever comes next. Think about the scale of time that this planet represents. 4 billion years. That is a number so large it loses meaning. 4 billion years of turning around the sun. 4 billion years of dust settling and winds blowing and ice forming and sublimating. 4 billion years of silence, except for the thin whisper of the wind and the occasional rumble of a rockfall or the crack of a volcano that has long since gone cold. In all that time, the small machines we have sent represent only the last few decades, a fraction of a heartbeat in the life of the planet. If a human mission lands in the 2030s or 2040s, that will be another heartbeat, a brief moment of warmth and noise and activity, and then perhaps silence again. Or perhaps not. Perhaps it will be the start of something longer. We do not know. The planet does not care either way. It just turns. And your own life, lying here in the dark, is smaller still, a flicker of consciousness in the vastness of time, and yet, here you are, able to picture this other world, able to ask this question, able to hold in your mind the image of a red point of light, and wonder about it. That is a remarkable thing. That is the thing that connects you to the Babylonians watching from their mud brick towers, to the Egyptians painting the red one on their temple walls, to the astronomers pointing their first telescopes at a tiny disk, to the engineers building rovers in clean rooms, to the astronauts who may one day stand on the surface and look back at the Earth and feel the weight of where they are. The wondering is the thread that runs through all of it. The wondering is what makes us human. You do not need to resolve the question tonight. You do not need to decide whether you believe humans will ever live on Mars. You do not need to pick a side or form an opinion or make a plan. You can just let the question rest. Let it float there in the back of your mind, soft and undemanding, like the red light itself floating in the dark sky. It will still be there tomorrow, and the day after, and the year after. The question is not going anywhere. Neither is the planet. They will both wait for you. So now, as your breathing slows even further, and your body sinks deeper into the bed, let the images we have gathered tonight begin to fade. the tan sky and the blue sunsets, the frozen water beneath the red soil, the buried habitats and the printed walls, the rovers rolling slowly across the plains, the thin wind and the cold and the radiation. Let them all soften, like colors in a photograph left too long in the sun. Let them become indistinct, a wash of feeling, rather than a list of facts. What remains is just the sense of a world, a real world, turning quietly in the dark. A world that is not ours, but that we have reached for anyway. A world that holds its secrets close. A world that does not promise us anything, but that invites us to wonder. Picture Mars now as it is, right now, in the quiet of space. The dust is settling on the plains. The polar caps are gleaming faintly in the dim sunlight. Phobos is racing across the sky, a dark, irregular shape against the tan. Deimos is drifting more slowly, a tiny speck of light if anyone were there to see it. The rovers are sleeping, their systems in low-power mode, waiting for the next soul's commands. The ancient riverbeds are dry and still. The volcanoes are silent. The whole planet is wrapped in its thin blanket of carbon dioxide, holding just enough warmth to keep the surface from dropping to the temperatures of deep space. It is a complete world, self-contained and whole, asking nothing of us, needing nothing from us. It just is. And you, lying here, are also a complete world, warm and breathing and alive, held by the gravity of your own planet, wrapped in the thick air that has protected you since the moment you were born. You are here, and you are safe, and you are slowly, gently drifting towards sleep. There is nothing you need to do. There is nowhere you need to go. The red point of light in the sky will keep its watch, as it has kept it for billions of years. The question of living there will keep its mystery. And you can rest now, in the stillness, in the quiet, in the soft dark of your own room, knowing that the wondering itself is enough. The wondering is the whole point. And tonight, the wondering can sleep. Let it sleep. Let yourself sleep. The small red world turns quietly in the dark, and all is still.